This is an audio recording for visually impaired students from the book Pardeep's Inorganic Chemistry, Volume 1 by Dr. K.K. Bhasin. Chapter 4 Ionic Solids. Most of the chemical compounds that we come across in our daily life are solids at room temperature. The particles constituting the solids may be atoms, ions, or molecules. One of the most important features of the solids is that the constituent particles are most closely packed. As a result, they possess strong intermolecular force of attraction. These strong molecular force of attraction accounts for the rigidity, definite shape, and definite volume in case of solids. Solids can be broadly divided into two types, the crystalline solids and the amorphous solids. A crystalline solid consists of regular arrangement of atoms, ions, or molecules throughout the crystal, whereas in case of amorphous solid, the regular arrangement of particles occurs over a small regions. In other words, a crystalline solid has the regular arrangement over a long range, whereas an amorphous solid has the regular arrangement over a short range. Crystalline solids can be classified into four major types depending upon first, the nature of the constituent particles, and second, the forces holding them together, bonding in the crystalline solid. These are shown in the table 4.1. Table 4.1 Classification of crystalline solids by the bonding. First, intermolecular bonding. Constituent molecules. Properties soft, low melting, volatile insulators. Common examples dry ice, CO2, iodine, acid, P4. Second, covalent network bonding. Constituent atoms. Properties hard, high melting, non volatile. Common examples diamond, C, quartz. Third, metallic bonding. Constituent positive ions and electrons. Properties variable in hardness and melting point, good conductors. Common examples all metals and alloys. Fourth, ionic bonding. Constituent positive ions and negative ions. Properties hard, high melting, conducts electricity in molten state. Common examples rock salt, NaCl, fluorite, CaF2. In this chapter, we shall discuss the bonding in solid crystals with special reference to ionic solids. First heading 4.1 Ionic bonds. An ionic bond is formed by the complete transfer of one or more valence electrons of one atom to the other atom so that both the atoms acquire the stable electronic configuration of the nearest noble gas. Compounds formed by this process of complete transfer of electron or electrons are called ionic compounds. The atom that loses the electron to form the positively charged ion is called the cation, and the atom that gains the electron to form the negatively charged ion is called the anion. Thus, an ionic bond is formed between the two positively charged ions, that is, between a cation and an anion, due to electrostatic force of attraction. The compounds containing ionic bonds are called ionic compounds. The electrostatic force F between the positively charged electrons or ions is governed by Coulomb's law. It is proportional to the product of two charges q1, q2 and inversely proportional to the square of the distance between them r square. That is, F is directly proportional to q1, q2 upon r square. This is known as inverse square law. It is important to note that the force F is not dependent upon the mass of the ions but depends only on the charges of the ions. When the distance between the positively charged ion is very small, the attractive force is balanced by the repulsive forces, which arises due to the interaction between the nuclei as well as the electrons of the two species. In brief, the electrostatic force of attraction which holds the positively charged ions together is known as ionic or electrovalent bond. Ionic bonds are formed by elements that readily form ions, thus metals in group 1 alkali metal and group 2 alkyne earth metals readily form positively charged ions cations, whereas the non-metals of group 16 and group 17 readily form negatively charged ions and ions. In addition, cations can also be formed by some of group 13 elements such as aluminium Al3 positive as well as by the transition metals. High atomic number elements of group 14 such as tin and lead also form cations. Example Sn2 positive and Pb2 positive and Sn4 positive and Pb4 positive ions. In group 15, nitrogen can form an anion N3 negative nitride ion. Ionic crystals are composed of an arrangement of infinite ions. The ions pack together in the crystal in such a manner that unlike charges come as close as possible, whereas like charges remain as far as possible. Such an arrangement maximizes the Coulombic attraction between oppositively charged ions and minimizes the repulsion arises from interaction between like charges. We therefore expect to find ionic compounds in the halides and oxides of the metals of group 1 and group 2, where the valence electrons from the metals are transferred to the non-metals. It is important to mention that lithium ion forms the ionic compound with nitride N3 negative ion, that is lithium nitride Li3N. General characteristics of ionic solids. The properties of ionic solids are different from those of covalent solids. Some of the characteristic properties of ionic solids are described below. First, crystalline nature. Ionic solids are crystalline in nature. X-ray studies reveal that ionic solids do not exist as molecules but consist of ions with opposite charges. The ions are arranged in a regular pattern. Each ion in the crystal is surrounded by a fixed number of oppositively charged ions. This fixed number is called the coordination number. The arrangement of ions in different ionic solids is different. For example, in sodium chloride, each Na positive ion is surrounded by 6 Cl negative ion and each chloride ion is surrounded by 6 Na positive ions. Second, hardness. Ionic solids are hard. The hardness of the ionic solids is due to the strong electrostatic forces of attraction between the positively charged ions. Hardness in ionic solids increase with decrease in the interionic distances and increase in ionic charge as shown in the table 4.2. An inspection of the table 4.2 reveals that LiF and MgO have the same interionic distance of 203 picometer. However, MgO is more harder because of the higher charge in MgO compared to LiF. Similarly, NaCl and CaS have nearly the same internuclear distance, that is 280 picometer, but CaS is more harder than NaCl because of the high charge on ions in CaS. In case of alkaline earth metal oxides MO, M is equal to Mg, Ca, Sr and Ba, the interionic distance increase in the group from magnesium to barium, although the ions are doubly charged. One can predict that the oxide with the minimum interionic distance should be harder MgO and the one with maximum interionic distance should be the least hard BaO. Third, high melting and boiling points. Ionic solids have relatively high melting and boiling points. Ionic solids have high melting and boiling point because of the strong electrostatic interaction between the cation and the anion. As a result, a large amount of energy is needed to overcome the interionic attractions to break the crystal lattice. This accounts for their higher melting and boiling points. The melting and boiling points of ionic solids depends upon the electrostatic force of attraction between the positively charged ions. The larger the electrostatic force of attraction, higher is the melting point. The magnitude of the forces of attraction depends upon the charges on the ions as well as ionic radii of ions. In other words, the closer the ions in the ionic crystal, the larger will be the attractive forces and higher will be the melting point. The melting points of some common sodium salts are tabulated in table 4.3. An inspection of the table reveals that the melting points decrease from NaF to NaI. This is because as the size of the anion increases, the corresponding force of attraction between the Na positive ion and the corresponding anion decreases. This results in the decrease of melting point. Thus, NaI has the least melting point in the halides. There is a significant difference between the melting point of NaCl 1073 Kelvin and BaO 1294 Kelvin, although the internuclear distance, table 4.2 between NaCl and BaO is nearly the same. The higher the melting point of BaO is attributed to the stronger interionic forces between the doubly charged Ba2 positive and O2 negative ions as compared to the attractive forces between the singly charged Na positive and Cl negative ion in case of NaCl. In general, ionic solids composed of small ions with high charges have the highest melting points. For example, Al2O3 melts at 2278 Kelvin. Fourth, brittleness. Ionic solids are brittle and are easily broken when a stress is applied on them. An ionic crystal is built up of closely packed ions of opposite charges. When a stress is applied to the ionic solid, there is a movement of layers of ions across the next layer. During this movement, the ions with similar charges come together as shown in figure 4.1. This causes strong repulsions among the similar ions and results in the breakdown of the crystal. Thus, ionic solids on the application of stress break down into powder easily. Fifth, conductance. Ionic solids do not conduct electric current at room temperature. In an ionic solid, the cation and the anion occupy the fixed positions in the lattice and are held together by strong electrostatic forces. It means that the ions are not free to move. As a result, ionic solids do not practically conduct electricity in the solid state. However, ionic solids in solution or molten state do not have a crystal lattice and the ions are not held together by strong electrostatic forces of at all. Thus, the ions are set free to move in an electric field. As a result, the ions conduct electricity due to their movement in the solution or in the molten state. Sixth, ionic reactions. Ionic solids, when dissolved in water, break down into a positively charged ions. When aqueous solutions of two ionic solids are mixed together, the positively charged ions combine instantaneously to give the product because of their immediate reaction. These reactions are quite fast. Seventh, solubility of ionic solids. Ionic solids are soluble in water and in polar solvents with high dielectric constant. Ionic solids are generally soluble in water. The dielectric constant of water is very high, 80. The role of dielectric constant is to decrease the electrostatic forces of attraction between the ions in an ionic solid. When an ionic compound is dissolved in water, the electrostatic forces of attraction between the ions reduced to 1 by 80, the force of attraction between the ions in the solid state. As a result, the ions get separated from one another and form a solution. The ions are now free to move. Another important feature of water is that it acts as a dipole with a positive and a negative end. When an ionic solid is dissolved in water, the positive end of the water dipole interacts with the negative ion of the ionic solid, while the negative end of the water dipole interacts with the positive ion of the ionic solid. As a result of the interaction between the ions and the solvent, a large amount of energy is released. This is called the hydrational energy. The amount of hydrational energy released is far more than the crystal energy of the ionic solid. As a result, the orderly arrangement of the ions in the crystal breaks and the ionic solid goes into the solution. It is important to mention here that the ionic solids do not dissolve in organic solvents because organic solvents are either non-polar or less polar and have low dielectric constant. Eighth, non-directional nature. In an ionic solid, the ions are arranged is in a perfectly regular way, repeating over and over again in all the directions. As a result, the electrostatic forces holding the ions together are uniformly distributed in all the directions around the ions. Thus, the bonding in ionic solid is non-directional. Next heading 4.2, close packing of spheres. The structure of many inorganic solids can be discussed in terms of the simple packing of spheres. The constituent atoms, ions, or molecule in a solid can be regarded as small hard spheres. In order to understand the packing of constituent particles in a crystal, it is assumed that these particles are hard spheres of equal size, which are spread over three dimensions. The packing of spheres take place as to fill the maximum possible available space. This type of packing is called close packing. The spheres of equal size can pack together as follows. First, linear arrangement. When the spheres are placed in a horizontal row touching each other, an edge of the crystal is formed as shown in figure. Second, two-dimensional packing. When the rows are combined touching each other, the crystal plane is formed. There are two ways in which rows can be combined. First, the spheres, when packed in the adjacent rows, packed together in such a way that the rows have horizontal as well as vertical alignment. In this type of arrangement, the spheres are known to form square close packing. Second, the spheres in every next row are placed in the depressions between the spheres of the first row. The spheres in the third row are vertically aligned with those in the first row. This type of packing gives a hexagonal pattern and is called hexagonal close packing HCP. A comparison of the two arrangements of spheres shows that in arrangement of the spheres in square close packing is less closely packed than in the arrangement of spheres in the hexagonal close packing. It has been calculated that in square close packing 52.4% of the available space is occupied in comparison to the 60.4% of the available space occupied by hexagonal close packing. Thus, hexagonal close packing is more efficient as more space is occupied by the spheres in this arrangement. The empty space left in square close packing is 47.6, 100 minus 52.4%. Whereas in case of hexagonal close packing, the empty space is 39.6, 100 minus 60.4%. This empty space is called void volume. In square close packing, the central sphere is in immediate contact with four other spheres, whereas in hexagonal close packing, the central sphere is in contact with six other spheres. The number of spheres with which the given sphere is in immediate contact is called the coordination number. Thus, the coordination number of each sphere in case of square close packing is 4, whereas the coordination number in case of hexagonal close packing is 6. If we look from above, the spheres in the close packed layer have curved triangular spaces between them. We shall consider them as triangles. If there are infinite layers of spheres, what is the ratio of number of spaces to the number of spheres? The answer is there are twice as many spaces as there are spheres. We can check the answer by counting the number of spaces around a sphere in the center of figure marked K. These are 6 spaces around the central sphere marked K. Let us now consider how many spheres are there around one space. It is easy to see that there are 3 spheres around one space. Thus, the number of spaces are twice the number of spheres. It is important to note that the number of spaces marked A are equal to the number of spaces marked by B. The spaces marked by A are those where the tips of the triangle points up the page, whereas the spaces marked B are those where the tips of the triangle points down the page. Both types of spaces are, however, equivalent. So far, we have discussed two-dimensional arrangement of spheres. We should remember that the hexagonal close pattern is more efficient than the square close pattern discussed above. Let us now consider the three-dimensional packing of spheres and the two types of voids between the spheres in the first layer as A and B. We have already mentioned that the voids A and B are equivalent. When a second layer of spheres is packed on the first layer A of spheres, it can be placed either on the voids A or on the voids B. It is not possible to place spheres on both type of voids simultaneously. It means that spheres of the second layer sit in half of the hollows of the first layer which have been marked A and B. The second layer B of spheres in the figure sits over the hollows marked with B. Now there are two types of voids in the second layer. These are marked C and D. The voids C are simply the voids which lie above the sphere of the first layer, whereas voids D are formed by the combination of the voids of the first layer A and the second layer of spheres B. The voids A and B of the first layer are triangular, whereas voids C of the second layer are only triangular. The voids D of the second layer are formed by the combination of two triangular voids, one from the first layer A and the second from the second layer B, with the vertex of one triangle upward and the vertex of the other triangle downward as shown in the figure. When we try to place the spheres in the third layer, there exist two possible positions where the spheres can be placed. Position 1, where the spheres can be placed corresponding to voids A in the first layer, while the second position is that where the spheres can be placed corresponding to voids D in the second layer. Thus, there are two ways in which spheres can be placed on the second layer to form the third layer. If the spheres of the third layer are placed on the void C of the second layer, the spheres go directly over the layer A. In other words, the third layer sits exactly over the spheres in the layer A. If this arrangement is continued, that is, repeated over and again, the stacking sequence of the layer is AB, 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 and so on. This type of packing is known as hexagonal close packing HCP and is shown in the figure 4.5 and 4.6. Metals like magnesium, molybdenum and beryllium crystallize in HCP. The actual arrangement of spheres in the hexagonal close packing is shown in figure 4.6. If the spheres of the third layer are placed on the octahedral voids D of the second layer, a new layer C is formed which is different from the layer A and the layer B. Thus the layer C is not directly over either A, which is different from layer A and the layer B. Thus the layer C is not directly over either layer A or layer B. If this type of stacking is continued, that is repeated over and again, a new sequence of layers is formed. This can be represented by ABC, 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 so on. This is known as cubic close packing CCP and is shown in figure 4.5 and 4.7. The actual arrangement of spheres in the cubic close packing is shown in figure 4.7. A close inspection of the figure 4.7 reveals that there is a sphere at the center of each face of the cube. Therefore, the cubic close packing CCP arrangement of spheres is given the alternative name as face-centered cubic arrangement FCC. Both types of packing discussed above, although different in shape, are equally economical. They occupy the maximum possible space, which is about 74% of the available volume. It is important to note that each sphere in the structure is surrounded by 12 equidistant neighbors, 6 in the same layer, 3 in the layer above and 3 in the layer below. Thus, the coordination number of an atom in a closed packed structure is 12. Most of the metals adopts either HCP or CCP structure. However, there are some metals that do not adopt a closed packed structure but have a slightly less efficient packing structure. One such structure is known as body-centered cubic arrangement. It is abbreviated as BCC and is shown in figure 4.8. In this structure, an atom in the middle of the cube is surrounded by 8 equidistant atoms at the corners of the cube. Thus, the coordination number of an atom in this type of packing is 8. In the body-centered cubic arrangement, about 68% space is filled by the atoms. It is definitely less efficiently packed than the CCP and HCP structures. Alkali and heavier alkyne earth metals adopts the BCC structure. There is an even simpler form of cubic packing known which is called simple or primitive cubic. This type of packing has 8 atoms at the corners of a cube. It simply occupies 52% the available space. Only one metal, polonium, is known to have this primitive cubic structure. The coordination number in this case is 6 and the structure is relatively loosely packed. Let us now summarize the characteristics of structures obtained by packing spheres of equal sizes. Structure simple cubic. Number of nearest neighbors 6. Packing efficiency 52. Number of spheres in the unit cell 1. Next, body centered cubic. Number of nearest neighbors 8. Packing efficiency 68%. Number of the spheres 2. Next, face centered cubic or cubic closed packed. Number of nearest neighbors 12. Packing efficiency 74%. Number of spheres 4. Hexagonal closed packing. Number of nearest neighbors 12. Packing efficiency 74%. Interstitial sites in closed packed arrangements. The arrangement of atoms in many elements and compounds in the solid state can be thought of in terms of close packing of similar spheres. The identical sphere packed themselves so closely that the available space is occupied to the maximum extent. The closer the packing, the greater is the stability of the crystal in both types of close packing, that is in HCP as well as in CCP. 74% of the available space is occupied by the spheres. The remaining 26% of the space in between the spheres remain unoccupied. This unoccupied space, also called the holes or voids in between the sphere, are called interstitial sites. There are two important types of interstitial sites. These sites are named depending upon the geometrical figure formed by the position of atoms surrounding the holes. As an example, in close packed arrangement of spheres, the centers of the three spheres lie at the vertices of an equilateral triangle. The empty space between these three touching spheres is called the triangular site. When a sphere in the second layer is packed above the three spheres touching one another, the type of site formed is called tetrahedral site. In fact, the site is bounded by four spheres with their centers arranged at the corners of a tetrahedral as shown in the figure 4.10. It is important to note that the shape of the hole is not tetrahedral, but it is the arrangement around the hole which is tetrahedral. The size of tetrahedral site is very much smaller than the size of the surrounding spheres. There is a second type of interstitial site in a close packed arrangement. This site is bounded by six spheres, which their centers located at the corners of an octahedron. These are called octahedral sites as shown in figure 4.11. It is clear from the figure that the octahedral site is formed by two sets of equilateral triangles which point in the opposite directions. Now a question arises, what about the relative size of octahedral and tetrahedral holes? The answer is that the octahedral holes are much bigger than the tetrahedral holes. This becomes clear when you think that it takes 6 spheres to enclose an octahedral hole and only 4 spheres to enclose a tetrahedral hole. Next heading 4.3 Ionic structures. In the previous section, we have discussed 4 different packing arrangements for identical spheres where hexagonal close packed, HCP cubic close packed, CCP or FCC, body centered cubic BCC and simple cubic SC. The same packing arrangements are also common among ionic solids. Ionic solids are formed from oppositively charged ions which different ionic radii and both kinds of ions must pack together. Generally, the anions are bigger than the cations and it is anions that form the array while the smaller cations fit in the holes called interstitial sites between the anions. Before we discuss the particular types of packing, it is important to consider the general principles that apply to ionic structure. First, ions are assumed to be incompressible and non-polarizable charged spheres. Second, ions try to surround themselves with as many as ions of opposite charges as possible and as closely as possible. Third, the cation to anion ratio must reflect the chemical composition of the compound. For example, the crystal structure of CaF2 must contain the arrangement of chloride ions with only half that the number of calcium cations in the crystal lattice. It is appropriate to recapitulate some of the terms that will be used in the crystal structure of ionic compounds. Ionic compounds have orderly arrangements of ions in the three dimensions. This regular arrangement of ions of crystalline solid in three-dimensional space is called space lattice. Space lattices are best described by a unit cell. A unit cell is defined as the smallest repeating unit in space which, when repeated over and again, produces the complete lattice. The unit cells of most ionic lattice are either cubic or distorted from cubic in some way. In any cubic unit cell, each corner ion is actually a part of 8 different cells. Therefore, such an ion contribute only as 1 by 8 ion for that cell. An edge ion is shared by 4 cells and contribute 1 by 4 of an ion. Similarly, a facial ion contribute half of an ion while the ion at the center of the cube contribute as a whole ion. Location of interstitial sites in cubic close packed arrangement. In many ionic lattices, the larger ions generally adopts one of the basic close-packed structures. As a result, the cations then occupy the interstitial sites. In case of a simple cubic type arrangement, there is a cavity at the center of each cube. A cation filling the cavity has 8 anions as nearest neighbors. It means that the cation has cubic coordination, that is, coordination number is 8. The common example is CsCl. The cations usually occupy the interstices of a face-centered cubic sublattice in the following two ways. First, if the cations occupy the body-centered position and or the 12 edge-centered positions, the coordination number of the cation is 6 for both the body-centered and edge-centered positions. As a result, these positions are referred as octahedral holes. Second, a cube can be subdivided into 8 equal subcubes. The subcube is called the cubelet. Each cubelet has 4 anions at the alternate corners. The cations can occupy all the 8 tetrahedral sites. Since the number of tetrahedral sites is twice the octahedral sites, it implies that there are 4 octahedral holes in face-centered cubic lattice. The 4 octahedral holes are of two types. One of the octahedral hole is filled by the body-centered atom, while the other octahedral hole are filled by the edge-centered atom as shown in figure 4.13. It is important to recall that the contribution of the body-centered octahedral hole is 1, whereas the total contribution of the edge-centered octahedral hole is 3, is equal to 12 into 1 by 4. Let us now discuss the crystal structure of some common ionic solids. Two important types of ionic solids corresponds to the general formula AB and AB2, where A and B represent the positively and negatively charged ions respectively. It is easy to draw the structure of pure elements, say the structure of sodium, than to draw the structure of compounds, for example, that of sodium chloride. This is because an element consists of only one type of atoms, whereas a compound contains at least two types of atoms, and all the atoms in the element occupy the lattice points. For example, copper has face-centered cubic structure. It means all the lattice points are occupied by the copper atoms. However, in case of even simple ionic compound AB, the arrangement of both the ions A and B has to described. Structure of ionic compounds of the type AB. Ionic compounds of the type AB means compounds where A and B represent the positively and negatively charged ions respectively in the ratio 1:1. Three most commonly found structures of the type AB are: first, sodium chloride or rock salt; second, zinc blende ZnS structure; third, cesium chloride CsCl structure. Let us now discuss these structures. First, structure of sodium chloride NaCl. Sodium chloride or common salt is probably the most familiar chemical of all. It is used by most of us on food or in cooking every day. The unit cell of sodium chloride is shown in figure 4.14. The sodium ions are represented by solid circles while chloride ions by hollow circles. The main features of the structures of sodium chloride are as follows. First, the chloride ions Cl negative are placed at the corners of the cube and at the center of each face. Thus, the chloride ions are arranged in the cubic close-packed CCP arrangement. This arrangement of chloride ions is also called face-centered cubic arrangement. Second, the sodium ions Na positive occupy all the octahedral sites. Third, each sodium ion Na positive is surrounded by 6 chloride ions Cl negative, and each Cl negative ion is surrounded by 6 Na positive ions. Thus, the coordination number of sodium ion is as well as chloride ion is 6. The crystal structure of sodium chloride in the figure 6.14 shows the 8 chloride ions Cl negative are present at the corners, whereas 6 chloride ions Cl negative are present at the faces of the unit cell. We know that each ion at the corner is shared between 8 unit cells and its contribution per unit cell is 1 upon 8. Similarly, the ion present on a face is shared by 2 unit cell and its contribution per unit cell is 1 upon 2. Thus, 8 Cl negative ions at the corners contribute 8 into 1 upon 8 is equal to 1 Cl negative ion per unit cell. 6 Cl negative ions at the faces contribute 6 into 1 upon 2 is equal to 3 Cl negative ions per unit cell. Total number of Cl negative ions per unit cell is equal to 1 plus 3 is equal to 4. An inspection of the diagram reveals that 12 Na positive ions are present on the edges, whereas one sodium ion Na positive sits inside the cell. We note that each ion present on the edge is shared by 4 unit cells and its contribution per unit cell is 1 upon 4, whereas the ion at the body center lies completely inside the cell and belongs entirely to the unit cell. Therefore, 12 Na positive ions at the edges contribute 12 into 1 upon 4 is equal to 3 Na positive ions per unit cell. 1 Na positive ion at the center of the unit cell contribute 1 into 1 is equal to 1 Na positive ion per unit cell. Total number of Na positive ions per unit cell is equal to 3 plus 1 is equal to 4. Thus, the stoichiometry of Na positive and Cl negative ions in the unit cell is equal to 4:4 or 1:1. It means that for each Na positive ion, there is only one Cl negative ion. This supports our 1:1 stoichiometry of NaCl. Sodium chloride type of structure is very common and is adopted by, first, most of the alkali metal halides excepting CSCl, CSBr and CSI. Second, most of the alkaline earth oxides and sulfides. Third, most of the halides of ammonium and silver. Second, structure of zinc sulfide. Zinc sulfide shows two types of structure known as, first, zinc blende structure and second, Wurtzite structure. A. Zinc blende structure. Zinc sulfide occurs naturally as the mineral zinc blende or sulfurite. The unit cell of zinc blende is shown in figure 4.15. The zinc ions are represented by the solid circles and the sulfide ions are represented by the hollow circles. The main features of the structure are detailed below. First, the sulfide ions S2 negative occupy all the corners of the cube as well as the center of each face. Thus, the S2 negative ions are arranged in the cubic close-packed type arrangement CCP. Second, the zinc ions Zn2 positive occupy half the tetrahedral sites. Third, there are 2 tetrahedral sites for each S2 negative. It means there are a total of 8 tetrahedral sites for 4 S2 negative ions. Of the 8 available tetrahedral sites, only 4 alternative sites are occupied by zinc ions Zn2 positive. The other 4 tetrahedral sites remain vacant. Thus, there are 4 Zn2 positive ions for 8 S2 negative ions, and the stoichiometry is 1:1. Fourth, an inspection of figure 4.15 reveals that each Zna2 positive ion is surrounded by 4 S2 negative ions which are directed towards the corners of a regular tetrahedron. Similarly, each S2 negative ion is surrounded by 4 Zn2 positive ions that are directed towards the corners of a regular tetrahedron. Thus, both the cations and the anions are present in the equivalent positions. As a result, the coordination in zinc blende is 4:4. Zinc blende type of structure is adopted by compounds such as CuCl, CuBr, CuI, AgI, and BeS. B. Wood-gite structure. It is another form of zinc sulfide that occurs in nature. The unit cell for the wood-gite structure is shown in figure 4.16. The Zn2 positive ions are represented by solid circles, and the S2 negative ions are represented by hollow circles O. Some of the line features of the structure are detailed below. First, the sulfide ions S2 negative are arranged in the hexagonal close-packed HCP arrangement. It means that the S2 negative ions are placed at the centers and corners of the two hexagons which are parallel to each other, and 3 more atoms in a parallel plane midway between the two hexagons. Second, the zinc ion Zn2 positive occupy half of the tetrahedral sites. Since there are 2 tetrahedral sites for each S2 negative ion, there will be a total of 8 such sites for 4 S2 negative ions. Out of the 8 sites available, only the 4 alternate sites are occupied by Zn2 positive ions. The remaining 4 sites are left vacant. Thus, the stoichiometry of the compound is 1:1. Third, it is clear from the figure 4.16 that each S2 negative ion is surrounded by 4 Zn2 positive ions which are directed towards the corners of a regular tetrahedron. Similarly, each Zn2 positive ion is surrounded by 4 S2 negative ions which are directed towards the corners of a regular tetrahedron. Thus, both Zn2 positive and S2 negative ions are present in equivalent position, and therefore the coordination of the compound is 4:4. Wood-gite type of structure is adopted by ZNO, CDS, CDSE, and BeO. Difference in zinc blende and wood-gite structure. It is important to note that the structure of wood-gite is very similar to that of zinc blende. The basic difference is that in case of zinc blende, the S2 negative ions are arranged in cubic close-packed HCCP arrangement, whereas in case of wood-gite, the S2 negative ions are present in hexagonal closed-packed HCP arrangement. Third, structure of cesium chloride CSCl. The structure of cesium chloride, like that of sodium chloride and zinc blende, is cubic. The unit cell of structure of CSCl is shown in figure 4.17. The cesium ions are represented by the solid circles, while those of Cl negative ions are represented by hollow circles. The line features of the structure of CSCl are detailed below. First, chloride ions Cl negative occupy all the corners of the cube. Thus, the Cl negative ions form a simple cubic arrangement. Second, cesium ions occupy the cubic interstitial sites, that is, each Cs positive ion sits at the body center of the cube. Third, there are 8 chloride ions Cl negative at the corners of the cube. Each Cl negative ion at the corner is shared between 8 unit cells, and its contribution is 1/8. Therefore, the contribution of 8 Cl negative ions at the corners will be 8 into 1/8 is equal to 1 Cl negative ion per unit cell. There is 1 Cs positive ion in the body center. It has its contribution 1 per unit cell. Thus, for each Cs positive ion, there is only 1 Cl negative ion. Therefore, the stoichiometry is 1:1. Fourth, each Cs positive ion is surrounded by 8 Cl negative ions, and each Cl negative ion is surrounded by 8 Cs positive ions. Thus, both type of ions are in equivalent position. Therefore, the coordination number of Cs positive and Cl negative ions are 8:8. Cesium chloride type structure is adopted by cesium bromide CsBr and iodide CSI, whereas cesium fluoride adopts the sodium chloride structure. This CsCl structure is observed only when the cations and anions are comparable size. Fourth, structure of calcium fluoride CaF2 or fluoride structure. The fluoride structure is named after the mineral fluorspar CaF2 calcium fluoride. The unit cell of CaF2 is shown in the figure 4.18. The calcium ions are represented by the solid circles, and the fluoride ions are represented by the hollow circles. The line features of the structure are detailed below. First, Ca positive ions occupy all the corners as well as the center of each face of the cube. Thus, Ca2 positive ions form cubic close-packed CCP arrangement. Second, the fluoride ions occupy all the tetrahedral sites, and each fluoride ion is surrounded by 4 Ca2 positive ions. Thus, the coordination number of fluoride ion is 4. Third, as there are two tetrahedral sites available for every Ca2 positive ion, the fluoride ions occupy all the tetrahedral sites. Thus, the stoichiometry of the compound is 1:2. Fourth, inspection of the structure reveals that each fluoride ion is surrounded by 4 Ca2 positive ions, whereas each Ca2 positive ion is surrounded by 8 F negative ions that are disposed towards the 8 corners of the cube. Thus, the coordination number of Ca2 positive and F negative ions in CaF2 are 8:4. Other examples of compounds that adopt the fluoride type structure are BaF2, BaCl2, SrCl2, CdF2, HgF2, and PbF2. Fifth, anti-fluoride structure. Several compounds with the formula M2X, especially the alkali metal oxides M2O, adopt the anti-fluoride structure. Anti-fluoride structure is just the reverse of fluoride CaF2 structure, in which the doubly charged anions, that is O2 negative ion, replace the calcium cation and the singly charged cation replace the fluoride ion. The unit cell of Na2O, which adopts the anti-fluoride structure, is shown in figure 4.19. The sodium ions are represented by the solid circles, whereas the oxide ions are represented by hollow circles. The line features of the structure are detailed below. First, the oxide ions O2 negative form the cubic close-packed CCP arrangement. It means the oxide ions O2 negative occupy all the corners as well as the center of each face of the cube. Second, the sodium ions occupy all the tetrahedral sites and are surrounded by 4 O2 negative ions. Third, there are 2 tetrahedral sites per atom in the close-packed arrangement. It means that there are 2 tetrahedral sites for every O2 negative ion. Thus, the stoichiometry of the compound is 2:1. Fourth, a careful inspection of the structure reveals that each Na positive ion is surrounded by 4 O2 negative ion, which are directed towards the corners of a regular tetrahedron. Each O2 negative ion is surrounded by 8 Na positive ions, which are directed towards the 8 corners of the cube. Thus, the coordination number of Na positive and O2 negative ions are 4:8 and 1:2. The anti-fluoride type structure is exhibited by alkali metal oxides such as Li2O, K2O, Rb2O. Let us summarize the structures of ionic solids that we described in the previous pages. Table 4.4, Summary of structures of ionic solids. Next heading 4.4, Radius ratio rule and coordination number. Ionic compounds are made up of positively charged A positive and negatively charged B negative ions. These ions are held together by electrostatic interactions. Each ion in an ionic compound is surrounded by a definite number of positively charged ions. For example, in the ionic crystal A positive B negative, the positively charged ion A positive is surrounded by a definite number of negatively charged ion B negative. Similarly, the negatively charged ion B negative is surrounded by a definite number of positively charged ions A positive. This definite number is called the coordination number. The coordination number of the cation and anion may be same or different. The coordination number depends upon the relative sizes of the ions. We have already learned that the arrangement of ions in a crystal depends upon the relative size of the ions or ratio of the radii of the ions. Thus, the radius ratio, which is the ratio of radii of positive and negative ions, determines the coordination number of the ions in an ionic solid. Radius ratio is equal to radius of positive ion upon radius of negative ion is equal to R positive upon R negative. Let us consider an ionic compound in which the positively charged ion A positive, shown by dark circle, is surrounded octahedrali by 6 negatively charged ions B negative, shown by hollow circle. For sake of simplicity, only 4 B negative ions are shown in figure 4.20 surrounding by A positive ion. In fact, there are 2 more B negative ions, one above and the other below the positively charged A positive ion. There are 3 possibilities of fitting the B negative ions around A positive is shown in figure 4.21. The most ideal arrangement corresponds to the situation in which all the anions are touching each other and the cation in turn is simultaneously touching all the anions as shown in figure 4.21. In this arrangement, overall attraction is maximum and the repulsion is minimum. In the second possibility, all the anions are not touching each other as shown in figure 4.21, whereas in the third possibility, the cation is rattling in the hole created by the anions as shown in figure 4.21. In both the second and third possibilities, the arrangement of ions are not proper. As a result, the attractive forces are smaller than the repulsive forces. Let us focus more on the stable arrangement shown in figure 4.21, where all the anions are touching each other and simultaneously with the cation. The radius ratio R positive upon R negative in this situation can be increased or decreased in two ways. First, either by changing the size of the cation, keeping anion same. Second, by changing the size of the anion, keeping cation same. Let us first study how the decrease in radius ratio changes the structure of the compound. If the size of the cation R positive is decreased, then the cation cannot touch the anion and this arrangement will be unstable. If the anions are made to touch the cation, the anions have to come more and more closer. This will cause mutual repulsion among the anions more than the arrangement will be unstable. If the anions are forced to touch the cation, a stage will come when one or more anions may be pushed away, with the result that the cation is surrounded ideally by lesser number of anions. This situation may result in a more stable structure by lowering the coordination number from 6 to 4. A similar situation can also arise by increasing the size of the anion. The students are advised to draw the structure of convenience themselves. On the other hand, the radius ratio R positive upon R negative can be increased either by increasing the size of the cation or by decreasing the size of the anion as shown in figure 4.23. In both the cases, the anions will not be touching one another, as a result not be touching one another. As a result, the attractive forces will be far less. If the radius ratio is further increased, the anion distance increases. This results in decreased anion electrostatic repulsion. If the anions are sufficiently apart from each other, a situation may arise when more anions may fit properly around a cation by increasing the coordination number from 6 to 8. This gives rise to a stable structure. In order to fit exactly the space between the 6 anions, the size of the cation has to be the size as shown by the shaded circle. By using Pythagorean theorem, we can calculate that the optimum ratio of cation to anion radius is 0.414. If the cation is larger than 1, giving the optimum 0.414 ratio, then the anions will be forced apart. In fact, this happens in most cases, and the increased anion distance decreases the anion electrostatic repulsion. When the radius ratio reaches 0.732, it is possible to fit 8 anions around the cation. On the other hand, if the radius ratio is less than 0.414, the anions will be in close contact and the cations will be rattling around in the central cavity. This does not represent a good arrangement. Instead of rattling, the anions rearrange to give smaller cavities surrounded by only 4 anions. A summary of the radius ratios and the packing arrangement is given in table 4.5. Table 4.5, the range of radius ratios in crystals. R positive upon R negative from 0.155 to 0.225. Coordination number 3, structural arrangement planar triangle, example boron oxide. Next, 0.225 to 0.414. Coordination number 4, structured arrangement tetrahedral, example ZNS. Next, 0.414 to 0.732. Coordination number 6, structural arrangement octahedral, example NaCl. Next, 0.732 to 0.999. Coordination number 8, structural arrangement cubic, example CSCl. Calculation of radius ratio. The most common and stable ionic lattices generally found are trigonal, planar, tetrahedral, octahedral, and cubic with coordination numbers 3, 4, 6, and 8 respectively. The size of the trigonal site is smaller than the size of tetrahedral site. Tetrahedral site is smaller than the octahedral site, which is smaller than the cubic site. The size of the site created by the surrounding ions can be easily calculated by using simple geometry. Let us calculate the radius ratio of various sites. First, radius ratio of trigonal site. A trigonal site is formed when 3 spheres are directed at the vertices of an equilateral triangle as shown in figure 4.24. Let us consider R positive and R negative be the radii of the cation and the anion respectively. In the equilateral triangle ABC, AB is equal to BC is equal to CA is equal to 2R negative. If D is the center of the triangle and assuming that the cation around D occupies the trigonal side, then BD is equal to R positive plus R negative. In the right angle triangle DBE, cos angle DBE is equal to BE upon BD is equal to R negative upon R positive plus R negative. Since angle BDE is equal to 30 degree because cos 30 degree is equal to root 3 upon 2. Thus, R negative upon R positive plus R negative is equal to root 3 upon 2. On inverting both the sides, 2 over root 3, 2 upon root 3 is equal to R positive plus R negative upon R negative is equal to R positive upon R negative plus 1, or R positive upon R negative is equal to 2 upon root 3 minus 1 is equal to 2 minus 1.732 upon root 3 is equal to 0.268 upon 1.732 is equal to 0.155. R positive is equal to 0.155 R negative. It means that the numerical value of the radius ratio for the trigonal side is 0.155. In other words, the radius of the cation should not be greater than 0.155 times of the anion. It has been found that only cationic boron B3 positive in boron oxide can fit into such a small site. Second, radius ratio for tetrahedral site. A tetrahedral site can be generated by placing spheres at the alternate corners of a cube as shown in figure 4.25. Let us consider that the four anions are present at the alternate corners of the cube and the cation occupies the tetrahedral site. As already discussed, the stable tetrahedral arrangement should be one where all the four anions are touching each other simultaneously with the cation. In the figure 4.25, however, the cation and the anions are shown at distant from each other. For sake of simplicity, let A be the length of each slide of the cube R positive and R negative be the radius of the cation and the anion respectively. The cation is shown in dark whereas anion are shown as hollow spheres. AC is the face diagonal whereas AD is the body diagonal of the cube. In the right angle triangle ABC, AC square is equal to AB square plus BC square, or AC is equal to root over AB square plus BC square is equal to root over A square plus A square is equal to root 2A. Also, AC is equal to R negative plus R negative is equal to 2R negative. So 2R negative is equal to root 2A, or R negative is equal to 1 upon root 2A. In the right angle triangle ACD, AD square is equal to AC square plus CD square. AD is equal to root over 2A square plus 2A square is equal to root 3A because AC is equal to root 2A. Thus, the sum of the radii of the cation and anion, that is R positive plus R negative, can be evaluated by taking half the length of the body diagonal AD. R positive plus R negative is equal to AD upon 2 is equal to root 3A upon 2. Dividing equation second by 1, we get R positive plus R negative upon R negative is equal to root 3A upon 2 by 1 upon root 2A. On rearranging, R positive plus R positive upon R negative plus 1 is equal to root 3 upon root 2. R positive upon R negative is equal to root 3 upon root 2 minus 1 is equal to root 3 minus root 2 upon root 2 is equal to 1.732 minus 1.414 upon 1.414 is equal to 0.318 upon 1.414 is equal to 0.225, or R positive is equal to 0.225 R negative. It means that the radius ratio for the tetrahedral side is 0.225. In other words, the radius of the cation should not be greater than 0.225 times the anion. Third, radius ratio for octahedral side. An octahedral side can be generated by the arrangement of 6 spheres formed by the arrangement of 4 spheres in one plane, one sphere on the top and one sphere at the bottom of the plane. A cross section through an octahedral side shows that 4 anions are at the corners of a square with the cation at the centers. One anion each at the top and bottom of the plane formed by the 4 anions also touch the cation. Suppose each side of the square ABCD is of length A. Let R positive and R negative be the radius of the cation and anion respectively. In the right angled triangle BCD, BC square is equal to CD square plus BD square is equal to 2R negative whole square plus 2R negative whole square is equal to 8R negative square, or BC is equal to 2 root 2R negative. Also, BC is equal to R negative plus 2R positive plus R negative is equal to 2R positive plus 2R negative. So, 2R positive plus 2R negative is equal to 2 root 2R positive. Dividing both sides by 2R negative, we get R positive upon R negative plus 1 is equal to root 2, or R positive upon R negative is equal to root 2 minus 1 is equal to 1.414 minus 1 is equal to 0.414. R positive is equal to 0.414 R negative. Radius ratio for cubic site. A cubic site is generated when 8 identical spheres occupy the 8 corners of the cube. This site is very similar to BCC packing, in which 8 anions sitting at the corners of the cube surrounded one cation at the center of the cube, as shown in figure 4.27. It is important to recall that the spheres are not shown touching one another. For sake of simplicity, let us assume the radii of the cation, anion, and length of the unit cell be R positive, R negative at A respectively. The length of the face diagonal AC can be evaluated from the right angle triangle ABC as AC square is equal to AB square plus BC square is equal to A square plus A square is equal to 2A square, or AC is equal to root 2A. AD is the body diagonal and can be evaluated from the right angle triangle ACD. AD square is equal to AC square plus CD square is equal to 2A square plus A square is equal to 3A square, or AD is equal to root 3A. The body diagonal AD is also given by AD is equal to R negative plus 2R positive plus R negative is equal to 2R negative plus 2R positive. On equating both the values of AD, we get R negative plus 2R positive is equal to root 3A, or R negative plus 2R positive is equal to root 3 upon 2A. We know from figure 4.27 AB is equal to 2R negative is equal to A, so R negative is equal to A upon 2. Dividing equation 1 and 2, we get R negative plus R positive upon R negative is equal to root 3 by 2A is root 3A by 2 upon A by 2, or 1 plus R positive upon R negative is equal to root 3, or R positive upon R negative is equal to root 3 minus 1 is equal to 1.732 minus 1 is equal to 0.732, or R positive is equal to 0.732 R negative. Thus, for the cation to occupy the cubic site of the anion, the radius ratio R positive upon R negative should not be less than 0.732. If the radius ratio is less than 0.732, then either the radius of the anion R negative is too large, or the radius of the cation R positive is too small. In both the cases, the anions have to come closer so that the cation and the anions may touch each other. This will result in the increased repulsion and the cubic arrangement will be less stable. This can be avoided by decreasing the number of anions surrounding the cation. If such a situation arises, the coordination number of the cation will decrease. As a result, the cubic site will become octahedral site. In other words, it amounts to saying that if R positive upon R negative is less than 0.732, the crystal would prefer to have octahedral geometry. It is clear from the above discussion how the radius ratio R positive upon R negative plays an important role in describing the crystal structure of ionic compounds. In brief, if the size of the cation is large, it will prefer to occupy larger hole, and if the cation is small, it will prefer to occupy a smaller hole. Next heading 4.5, limitations of radius ratio rule. We have noted that the radius ratio rule is very helpful in understanding the structures of anionic compounds. It is also a very useful guide to predicting the structures of unknown ionic compounds. However, this rule also has got several limitations and predict wrong structures in some cases. The limitations to the radius ratio rule arises because, first, each ion is considered to be a hard inelastic sphere. This is not a correct assumption because anions compared to cations are not hard. In fact, anions are bigger in size and are more polarizable under the influence of the cations. The extent to which the anions are polarized depends upon the polarizing capacity of the cation. The more the anion is polarized, the more is the covalent character introduced in the ionic bond. Let us take an example of AgI crystal. The radius ratio Ag positive in case of AgI is 0.52. It indicates R Ag positive upon R I negative is equal to 1.12 Armstrong upon 2.16 Armstrong is equal to 0.52. The coordination number 6 corresponding to NaCl structure. However, AgI is a 4 coordinated tetrahedral lattice with zinc blende structure. Similarly, radius ratio in case of ZNO, HDS and CDS is calculated to be greater than 0.5, indicating coordination number 6, but these crystals have tetrahedral structure. Second, radius ratio rule fails to explain why some compounds crystallize in more than one modification with different coordination numbers. For example, thallium chloride TlCl crystallizes out in NaCl structure with coordination number 6 with internuclear distance 315 picometer. It has also been found to adopt CSCl structure with coordination number 8 with internuclear distance 332 picometer. Third, radius ratio rule suggests 8 coordinated CSCl structure for the oxides of larger divalent metal ions such as Ba2 positive, Sr2 positive, and Pb2 positive. However, in reality, no 8 coordinated metal oxide MO have been experimentally found. Fourth, the effective radius of the cation depends upon the nature of the anions surrounding it. This can be clearly seen in table 4.6, which lists some of the inter-ionic distance found in AgX and NaX compounds having the NaCl crystal structure. Both AgF and NaF are known to crystallize out in NaCl type of structure with coordination number 6. It shows that the size of Ag positive ion is bigger than Na positive ion if the size of F negative ion is taken as constant. On the other hand, AgCl and NaCl also crystallize out in NaCl type of structure. It means that the size of Na positive ion is bigger than that of Ag positive ion. We take the size of Cl negative ion in both the cases constant. This can be easily understood as Ag positive ion is softer than Na positive ion and introduces relatively more covalent character with polarizable anions like Cl negative or Br negative. These changes in the size of cations can introduce errors in the radius ratio rule calculations, and predictions made on the basis of this may prove wrong. Next, heading 4.6, lattice energy. Lattice energy of an ionic solid is a measure of the forces of the attraction between the ions and in the solid state. It helps in determining the stability of the ionic crystal. Lattice energy of a solid U is defined as the amount of energy that is released when 1 mole of ionic crystal is formed from the gaseous ions. The formation of 1 mole of the ionic crystal from the gaseous ions may be represented as M positive plus X negative gives out Mx. Delta H is equal to lattice energy U. The higher the value of lattice energy, the stronger is the ionic bond. The lattice energy in case of sodium chloride is minus 782 kJ per mole. The negative sign indicates that the reaction is exothermic and energy released in the formation of sodium chloride crystal from the gaseous sodium and chloride ions. The lattice energies for some typical ionic compound are given in table 4.7. An inspection of table 4.7 reveals that the lattice energy of an ionic crystal depend upon the size and charge of the ions. An increase in the charge of ion keeping the size of the ion constant increase the lattice energy. For example, the lattice energy of MgCl2 is much greater than the lattice energy of LiCl. Than the lattice energy of NaCl, although the ionic radii of S2 184 picometer and Cl negative 181 picometer are about the same. An increase in the size of cation keeping the charge of the ion constant lowers the lattice energy of the crystal. It is evident from the values of lattice energies of LiCl, NaCl and KCl. An increase in the size of the anion results in the decrease of lattice energy. It is evident from the values of lattice energies of NaCl and NaBr, Na2O and Na2S. Compounds containing 2 positive or 2 negative ions have very high lattice energies and are very stable, as shown in the case of MgO and MgS in table 4.7. Calculations of lattice energies of ionic solids. The lattice energy of ionic solids can be calculated by taking into consideration 2 types of interaction between the ions present in the crystal. These are: first, attractive interaction between a positively charged ion. Second, repulsive interaction due to interpenetration of electron charge clouds. Let us now investigate these interactions one by one. First, attractive forces between a positively charged ions. The potential energy of a pair of a positively charged ion varies inversely as the distance r between the ions. Mathematically, the attractive potential energy can be expressed as PE attraction is equal to Z1E into minus Z2E upon R, where E is electronic charge, R is equal to internuclear distance between ions. Z1 and Z2 are the charges on the cation and anion. In case of NaCl, Z1 is equal to 1 and Z2 is equal to 1. For MgO, Z1 is equal to 2 and Z2 is equal to 2. For CaCl2, Z1 is equal to 2 and Z2 is equal to 1. Second, repulsive interactions due to interpenetration of electron clouds. When the cations and the anion approach very close to each other, the electron cloud of adjacent ions begin to overlap. In other words, electron clouds of the cation and the anion interpenetrate into each other, and this results in the electron-electron repulsion. The penetration energy due to repulsion interaction is inversely proportional to the nth power of distance r between the ion. It may be expressed as Pe repulsion is equal to Be square upon Rn, where E is electronic charge, B is equal to repulsion coefficient, N is equal to a constant known as bond exponent. The value of N increases with the increase in the electron density around the ion. The value of N is a function of electron configuration. The average value is taken for ion pairs having ions with different N values. The net potential energy for a pair of ions with opposite charges is given by sum of the two terms given by equation 4.1 and 4.2. Pe net is equal to Pe attraction plus Pe repulsion is equal to minus Z1 Z2 E square upon R plus B E square upon R power N. The equation 4.3 is known as Bohm equation and gives the net potential energy for a pair of ions when the ions are brought together from infinite distance. The energies corresponding to the attractive and repulsive interactions between two ions are plotted in figure 4.28. It also clear from the figure that the repulsive interaction Be square upon R power N increase more rapidly than the attractive interactions between the two ions as the value of interionic distance R decreases. The total potential energy shown by the solid line decreases and has a minimum value at a distance known as equilibrium distance R0. In brief, the boron equation 4.3 calculates the energy released when a cation and an anion separated by an infinite distance in the gaseous state are brought together at a distance r from each other. Average value are used. Example, in LiCl, Li positive is equal to 5, Cl negative is equal to 9, thus the LiCl N is equal to 5 plus 9 upon 2 is equal to 7. At the equilibrium distance R0, all the interactions must be taken into consideration. In an ionic crystal, there are a large number of cations and anions which are packed closely together in solid state. It means that the force acting on particular ion will not be determined solely by the positively charged ion immediately surrounding it, but also by other ions, both positive and negative, at greater distance. To understand the various forces of attraction and repulsion, let us take the specific example as of a well-known crystal system of sodium chloride NaCl. As shown in the figure 4.29, each sodium ion is surrounded by first 6 Cl negative ions at a distance r. Second, 12 Na positive ions at a distance root 2r. Third, 8 Cl negative next square ions at a distance root 3r. Fourth, 6 Na positive next square ions at a distance 2r. Fifth, 24 Cl negative next square ions at a distance root 5r, and so on. The first term in the Bohr equation corresponding to the energy released due to attraction in bringing a sodium ion in the crystal lattice of sodium chloride from infinity is given by the summation of all interaction. Pe is equal to minus 6 Z1 Z2 E square upon R plus 12 Z1 Z2 E square upon root 2R minus 8 Z1 Z2 E square upon root 3R plus 6 Z1 Z2 E square upon 2R minus 24 Z1 Z2 E square upon root 5R plus and so on is equal to minus Z1 Z2 E square upon R into 6 minus 12 upon root 2 plus 8 upon root 3 minus 6 upon 2 plus 24 upon root 5 and so on. It is important to note the potential energy due to attraction is given a negative sign because energy is lowered, while the potential energy due to repulsion is given a positive sign because energy is increased. The quantity in the bracket is the summation of an infinite series and is known as Moudon constant. The Madelung constant is an expression of all the electrostatic interaction, both attractive and repulsive, per mole of the solid. It is by convention given the symbol A. In case of sodium chloride, the value of Madelung constant has been found to be 1.747558. The numerical value of Madelung constant depends upon the geometry of the crystal. As a result, this value will be same for all compounds which display sodium chloride structure. The value of Madelung constant can be calculated for other crystal system in the same way from the geometrical arrangement of the ions in the crystals. The expression 4.5 can be simplified as Pe is equal to minus A Z1 Z2 E square upon R, where A is equal to 6 minus 12 upon root 2 plus 8 upon root 3 minus 6 upon root 6 upon 2 plus 24 upon root 5 and so on. The value of Madelung constant for some common crystal structure are given in table 4.9. Table 4.9 Madelung constant A for 5 common crystal systems. Sodium chloride, formula NaCl, coordination number Na positive 6, Cl negative 6, A 1.74756. Cesium chloride, formula CaCl, coordination number S positive 8, Cl negative 8, A 1.76276. Next, zinc blend, formula ZnS, coordination number Zn2 positive 4, S2 negative 4, A 1.63805. Next, wurtzite ZnS, Zn2 positive 4, S2 negative 4, A 1.64132. Next, fluorite, formula CaF2, coordination number Ca2 positive 8, F negative 4, value of A 5.03878. The second term in the potential energy expression 4.3 is due to the overlap of electron clouds of the adjacent ions. This results in electron-electron repulsion due to the interpenetration of electron clouds. Since the repulsion varies inversely to the nth power of the distance between the ions, only the nearest neighbors are taken into consideration. In the crystal structure of NaCl, each sodium is surrounded by 6 chloride ions. Therefore, the repulsion coefficient is taken as 4b instead of b for sodium chloride. Thus, the repulsive energy term Be square upon R power n in the expression 4.3 becomes 6Be square upon R power n. Thus, the potential energy can be modified as Pe repulsion is equal to Be square upon R power n, where B is equal to 6B for NaCl. Taking into consideration the modified attractive 4.6 and repulsive interaction 4.7, the expression 4.3 can be reframed as Pe is equal to minus A Z1 Z2 E square upon R plus Be square upon R power n. The expression 4.8 defines the net potential energy of an ion that takes into consideration all types of electrostatic attractive and repulsive interaction due to the neighboring ions in the crystal lattice. It can be further simplified if we replace Z1 is equal to Z2 is equal to Z for sodium chloride type crystals at the equilibrium internuclear distance R0. The attractive and repulsive forces are exactly balanced and it corresponds to minimum potential energy. P is equal to minus A Z square E square upon R0 plus Be square upon R0 power n. Equation 4.9 can be rewritten as P is equal to minus A Z square E square R0 power minus 1 plus Be square R0 power minus n. Differentiating equation 4.10 with respect to R, we get d upon drPe is equal to minus Az square E square minus 1 R0 power minus 2 plus Be square minus n into R0 power minus n minus 1 is equal to Az square E square R0 power minus 2 minus n Be square R0 power minus n minus 1. At equilibrium, d upon drPe is equal to 0 and the equilibrium distance r is equal to r0. So the expression 4.11 becomes Az square E square R0 power minus 2 is minus n Be square R0 power minus n minus 1 is equal to 0, or Az square E square R0 power minus 2 is equal to n Be square R0 power minus n minus 1. On rearranging, B is equal to Az square E square R0 power minus 2 upon n E square R0 power minus n minus 1, or B is equal to Az square upon n into R0 power minus 2 plus n plus 1 is equal to Az square upon n into R0 power n minus 1. Similarly, R0 can be expressed as R0 power n minus 1 is equal to nB upon Az square. R0 is equal to nB upon Az square power 1 upon n minus 1. Substituting the value of B in expression 4.9, we get P is equal to minus az square e square upon r0 plus az square e square r0 power n minus 1 upon n into r0 n is equal to minus az square e square upon r0 plus az square e square upon n r0 power n minus n plus 1 is equal to minus az square e square upon r0 plus az square e square upon n r0 is equal to az square e square upon r0 into 1 by n minus 1 is equal to minus a z square e square upon r0 into 1 minus 1 upon n. The lattice energy U0 is defined as the energy released in the formation of 1 mole of the crystal from the gaseous ions which are separated from each other by infinite distances. Thus, the expression 4.14 when multiplied by Avogadro number n gives the lattice energy for 1 mole of the ion pair. So, U0 is equal to minus n0 into a z square e square upon r0 into 1 minus 1 upon n. The above expression 4.15 is known as Born-Land equation. This is an important relation as it allows the lattice energy to be calculated from a knowledge of the geometry of the crystal, the Madelung constant, the charges and the inter-ionic distances. It is important to note that lattice energies of ionic compounds are always negative. Several important conclusions can be drawn from Born-Land equation which are as follows. First, the higher the charge on the cation and anion, the higher is the value of lattice energy, and this confirms the stability of the crystal. Second, the smaller internuclear distance, the greater is the lattice energy of the crystal. Third, the higher the value of A Madelung constant, the greater is the value of lattice energy. Fourth, the higher the value of N Born exponent, the greater is the value of lattice energy. A comparison of the lattice energies calculated from the Born-Land equation with the experimental values reveal that there is a fairly good agreement. However, the Born-Land equation has several limitations because the equation assumes both the cation and the anion as incompressible solids with spherical shape. Born-Land equation is not in good agreement in cases where the ions tends to distort, that it is in case where there is increasing covalent character. Now there are few examples based on application of Born equation. Importance of lattice energy. In an ionic crystal, the ionic are held together by strong electrostatic force. The electrostatic forces between the positively charged ions are governed by Coulomb's law and is proportional to the product of the two charges Q1, Q2 and inversely proportional to the square of the distance between them r square. That is, F is directly proportional to Q1, Q2 upon r square. The force F is not dependent upon the mass of the ions but only on the charges. When the distance between the positively charged ion is very small, the attractive force is balanced by the repulsive force due to interaction between the nuclei as well as the electrons of the two ions. Because of the strong forces between the ions in the ionic crystals, ions are not free to move about. As a result, ionic crystals are usually poor conductor of electricity. If the ionic crystal is heated to melt, the crystal lattice is broken down and the ions become free to move in an electric field and therefore carry current and become a good conductor of electricity. The energy required to break the lattice and to set the ions free is called lattice energy. This energy depends upon the strength of ionic bond, which is in turn depends upon the ion size and charge. Thus, lattice energy is helpful in explaining first, stability of ionic bond. The greater the lattice energy, the greater is the stability of the ionic bond. This is because more energy is needed to separate the positively and negatively charged ions. For example, magnesium oxide with dipositive ions Mg2 positive and O2 negative has a much higher lattice energy 3795 kJ per mole than sodium fluoride 915 kJ per mole with a monopositive and mononegative ions Na positive, F negative. Therefore, magnesium oxide is more stable than sodium fluoride. Second, melting points. Ionic crystal with high lattice energy require a large amount to break the crystal. As a result, ionic compounds possess high melting points. Third, hardness. Ionic crystals with a high lattice energy are very hard. Hardness is determined on Mohs scale. Mohs scale of hardness was defined by Friedrich Mohs. According to his scale, the hardest material diamond is assigned a value of 10, whereas the softest material talc is assigned a value of 1. Table 6.10 complies the hardness of ionic crystals, which depends upon the inter-ionic distances. The smaller the inter-ionic distance, the harder is the ionic crystal. Next heading 4.7 Born-Haber cycle for lattice energies. The lattice energies of a crystal is defined as the amount of the energy released when 1 mole of the ionic crystal is formed from the gaseous ions. M positive plus X negative gives out Mx. U is equal to lattice energy. It is not possible to determine the lattice energies of crystals directly. However, experimental values can be obtained by relating the lattice energy of a crystal to other thermodynamical data using the cycle devised by Born and Haber in 1919. A Born-Haber cycle is the application of Hess laws, which states the enthalpy of a reaction is the same whether the reaction takes place in one step or in several steps. As an example, let us consider the energy changes during the formation of sodium chloride from elemental sodium and gaseous chlorine. Na plus half Cl2 gives out NaCl. Delta HF is equal to heat of formation. The reaction between sodium and chlorine gas to form sodium chloride can be broken down into the following 5 steps. Step 1. Vaporization of sodium metal. The energy required to convert 1 mole of metallic solid into the gaseous sodium is called sublimation energy S. Na plus S gives out Na. S is equal to sublimation energy. Step 2. Dissociation of chlorine molecule ion chlorine atoms. The amount of energy required to convert 1 mole of the gaseous chlorine molecule into atoms is called dissociation energy. It is represented by D. Cl2 plus D gives out 2Cl. The energy required for producing 1 mole of gaseous chlorine atom is D by 2. Half Cl2 plus D upon 2 gives out 1Cl. D by 2 is equal to dissociation energy. Step 3. Ionization of sodium vapors. The amount of energy required to convert 1 mole of the gaseous atom into gaseous sodium ions is called the ionization energy IE. Na plus IE gives out Na positive plus E negative. IE is equal to ionization energy. Step 4. Conversion of gaseous chlorine atom to gaseous chloride ion. The amount of energy released to convert 1 mole of the gaseous chlorine atom into gaseous chloride ion is called the electron affinity EA. Cl plus electron gives out Cl negative plus Ea. Ea is equal to electron affinity. Step 5. Combination of gaseous sodium ion with gaseous chloride ion to form solid sodium chloride. The amount of energy released when 1 mole of solid sodium chloride is obtained from gaseous sodium and chloride ions is called lattice energy. It is represented by UO. Na positive plus Cl negative gives out NaCl plus UO. UO is equal to lattice energy. The energy changes in the formation of solid sodium chloride from solid sodium and chlorine gas, the summarized graphically in figure 4.30. A cycle of changes like the one shown in figure 4.30 is called Born-Haber cycle. According to Hess laws, the heat of formation of 1 mole of sodium chloride should be the same whether the reaction takes place directly in one step or indirectly in several steps. Thus, delta HF is equal to S plus half D plus IE plus EA plus UO, or UO is equal to delta HF minus S minus half D minus IE minus EA. The lattice energy UO of solid sodium chloride can be calculated with the help of other thermochemical quantities that can be easily measured experimentally. Next heading 4.8 Applications of Born-Haber cycle. Born-Haber cycle is very useful in calculating important parameters such as electron affinity, proton affinity, lattice energy, etc. Let us know how it helps in evaluating the following. First, calculation of heats of formation. Born-Haber cycle is very useful in calculating the heats of formation of unknown compounds. Heat of formation of compound determines the stability of the compound. The heat of formation of MCl type crystals, say NaCl, is given by the expression delta H is equal to S plus half D plus IE plus EA plus UO. Similarly, the heat of formation of MF2 type crystals, say CaCl2, is given by the expression delta HF plus S. Delta HF is equal to S plus D plus IE1 plus IE2 plus 2EA plus UO, where IE1 and IE2 represent the first and second ionization energies of the element M. If the heat of formation delta HF is negative, the reaction is exothermic and the compound formed will be stable. If the heat of formation delta HF is positive, the reaction is endothermic and the compound formed will be unstable. This can be easily explained by NaCl2 is not formed, whereas NaCl is easily formed by setting up the Born-Haber cycle for the compounds NaCl2 and NaCl. The cycle shows that the formation of NaCl is an exothermic reaction, whereas the formation of NaCl2 is an endothermic reaction. As a result, NaCl2 is not formed, although it has higher lattice energy than NaCl. The formation of NaCl2 is not favored primarily due to the very high value of second ionization potential of sodium, because that relates to the removal of inner shell electron. The second ionization energy of sodium is very large compared to the large negative lattice energy. Similarly, Born-Haber cycle explains the formation of CaCl2 in preference to CaCl in a reaction between elemental calcium and gaseous chlorine molecule. This is because the energy involved in the double ionization of Ca to Ca2 positive is more than compensated by the very large lattice energy of CaCl2. In case of CaCl, although the energy required for the ionization of Ca to Ca positive is small, the lattice energy of CaCl is very small. The energies involved in the formation of CaCl and CaCl2 are tabulated in table. An inspection of the table 4.11 reveals that the energies of formation of CaCl2 is much more than of CaCl. Consequently, CaCl2 is far more stable than CaCl. In fact, CaCl2 is the only chloride known of calcium. Second, calculation of electron affinities. Electron affinities can be measured directly only for conversion of atoms into singly charged ions. For example, the affinity of oxygen for the electron can be expressed as O plus electron gives out O negative plus Ea. The concept of electron affinity can also be extended to ions. For example, addition of electron to a negatively charged ion can be expressed as O negative plus electron plus 708 kilojoule gives out O2 negative. Electron affinity of an anion is always negative. This is because the incoming electron is repelled by the negative charge of the anion, and energy must be added to force the electron to add on a negative ion. For example, the addition of second electron to an O negative ion to form an O2 negative ion requires 708 kilojoule per mole of energy. The energy needed to force an electron into an O negative ion is greater than energy given off when an electron is added to an oxygen atom to form the O negative ion. O plus electron gives out O negative plus 141 kilojoule. It is important to note that the electron affinity of the anion cannot be determined directly. As a result, indirect methods are used to determine the electron affinity of the anions. Born-Haber cycle is specially used in calculating the electron affinities of some elements and anions which are difficult to determine directly. For example, in case of calcium oxide CaO, the heat of formation can be expressed as delta HF is equal to S plus half D plus IE plus EA plus UO. On rearranging, electron affinity is given by EA is equal to delta HF minus S minus half D minus IEA minus UO, where S sublimation energy, delta HF heat of formation, D dissociation energy, and IA ionization energy can be determined experimentally, while UO lattice energy can be calculated by using Born-Lehn equation. Third, determination of proton affinity. Proton affinity PA is defined as the enthalpy change in a reaction where a proton is added to a gaseous species A. For example, A plus H positive gives out AH positive. Delta H is equal to PA. The enthalpy change can be obtained from suitable thermochemical cycle provided the lattice energy is known. We can determine the proton affinity of ammonia. NH3 plus H positive gives out NH4 positive by constructing the Born-Haber cycle as shown in figure. The enthalpy change for the overall reaction is given by delta HF is equal to D plus IE plus EA plus PA plus UO. On rearranging, the proton affinity PA of ammonia can be determined by the expression PA is equal to delta HF minus D minus IE minus EA minus UO by substituting the known values of delta HF, D, IE, EA and UO. Delta HF is equal to minus 144.3 kilojoule per mole. D is equal to 430.9 kilojoule per mole. IE is equal to 1311.6 kilojoule per mole. Ea is equal to minus 347.2 kilojoule per mole. UO is equal to minus 648.5 kilojoule per mole. We get Pa is equal to minus 144.3 minus 430.9 minus 1311.6 plus 347.2 minus 648.5 is equal to minus 891.1 kilojoule per mole. Thus, the proton affinity of ammonia is minus 891.3 kilojoule. The negative value indicates that the reaction is exothermic. By constructing suitable thermochemical cycles, we can calculate the proton affinities for phosphonium pH4 positive, aerosonium ASH4 positive, hydroxonium ions H3O positive, etc. Now there are some problems or the examples based on Born-Haber cycle. Next heading 4.9, solvation energy and solubilities of ionic compounds. Solubility of ionic compounds in different solvents depends upon the lattice energies of the solid. Ionic solids are generally soluble in polar solvents like water, ethanol, or tetrahydrofuran (TH4), THF, but are insoluble in non-polar solvents such as carbon, tetrachloride, benzene, or hexane. In order to dissolve an ionic solid in a polar solvent, the attractive forces holding the ions together, that is lattice energies in the solid, must be broken down. The energies required to break down the attractive forces between the ions in the solid comes from the strong interaction between the cation and anions of the ionic solid with the opposite ends of the polar solvent molecules. This strong interaction between the cation and anions of the ionic compounds with the solvent molecule result in the solvation of the ions, that is, the ions are surrounded by solvent molecules. Solvation of ions is a bond making process and hence energy is released in the process. Thus, solvation is an exothermic process and releases a lot of energy. This release of energy is called solvation energy. When water is used as a solvent, the corresponding energy is called hydrational energy. The amount of energy released during the solvation of ions depends upon the dielectric constant of the solvent. The dielectric constant of water is 80 at 25 degrees Celsius. It means that when an ionic compound dissolves in water, the attractive forces between the ions are reduced to 1 upon 80 of the force between the ions separated by the same distance in vacuum. Thus, solvents which cause greater solvation of ions and release higher solvation energy are good solvents for ionic solids. Good solvents for ionic substance usually have high dipole moments and high dielectric constant. Next heading 4.10, polarizing power and polarizability. The type of bond between two oppositively charged ions, A positive and B negative, depends upon the effect of one ion on the other ion. The positive ion attracts the electrons on the negative ion and at the same time repels the nucleus. This results in the distortion of the negative ion. In other words, the negative ion is polarized. The negative ion can also polarize the positive ion. Since the anions are larger than cations and therefore their electron clouds are less tightly held, as a result, the distortion effect of the larger ion on a small one will be less pronounced. If the degree of polarization is very small, then the bond between the ions A positive and B negative remains largely ionic. However, if the degree of polarization is large, electrons are drawn from the negative ion towards the positive ion. This results in the high concentration of the electrons between the two nuclei and is responsible for the covalent character. For example, the large iodide ion is spherical symmetrical. However, when a small positively charged ion comes close to the iodide ion, the electron cloud of the larger iodide ion is pulled towards the lithium ion. The iodide ion is said to be distorted or polarized. The power of an ion to distort the other ion is called its polarizing power, and the tendency of the ion to distortion is known as polarizability. The polarizing power increases as ions become smaller and highly charged. In other words, the polarizing power of a cation is proportional to charge upon radius ratio. The polarizability of the negative ion is greater than that of positive ion because of difference in the effective nuclear charges. Large negative ions are more polarizable than small ions. Fazan's rules. Kashmir Fazans developed the following four rules that summarizes the factors favoring polarization of ions that results in the covalent character. First, a small positive ion favors covalency. Second, a large negative ion favor covalency. Third, large charges on either ion or on both the ions favor covalency. Fourth, if the positive ion does not have a noble gas configuration, then the covalency is favored. Let us explain all these rules one by one with example. First, a small positive ion favors covalency. In small positive ions, the charge is concentrated over a very small region. This makes the positive ion high polarizing. It can therefore distort the negative ion effectively, which results in the increased covalent character of the ionic bond. Thus, smaller the size, the greater is the polarizing power. Thus, polarizing power of the cation decreases with increase in the size of cation. This can be easily illustrated by considering the metal chlorides of group 2 as given in table 4.12. It is clear from the table that the ionic size increases down the group 2 elements. As a result, Be2 positive is most polarizing, whereas Be2 positive is practically not polarizing. As a result, the covalent character decreases down the group 2 elements. One of the most convenient method of distinguish ionic behavior from covalent behavior is by observing the melting point. Ionic compounds tend to have high melting points than the covalent compounds. Thus, the low melting point of BeCl2 in comparison to the other alkaline earth metals is mainly due to its more covalent character. Second, a large negative ion favors covalency. The polarizability of the anion increases with increase in size of the anion. This is because the electron cloud of a large sized ion is less strongly held by the nucleus. Consequently, it can be easily polarized by the cation. Thus, larger the anion, the higher will be the polarizability, and as a result, more will be the covalent character of the bond. This can be illustrated by considering the various halides of potassium ion. As the size of the anion increases from F negative to I negative, the covalent character of the potassium salt increases. This can be easily reflected by the low melting point of Ki. Third, large charge on either ion. We have already discussed that the polarizing power of a cation and the polarizability of the anion increases with increase in the charge of the respective ion. It means that highly charged cation will extend greater effect in polarizing the anion, whereas the highly charged anion will be effectively polarized. This can be illustrated by considering that the radii of Na positive and Ca2 positive ions, which are nearly similar. However, because of higher charge on Ca2 positive, CaCl2 has more covalent character and consequently low melting point than sodium chloride as given in table. Fourth, noble gas configuration. Cation with 18 electron shell configuration, pseudo-noble gas configuration cause greater polarization than such cations with 8 electron shell configuration with the same size and charge. It is primarily because in case of 18 electron shell ion, there are 10 d electrons apart from 8 s and p electrons. The d electrons do not shield the nuclear charge effectively. As a result, the cation will exert a higher nuclear charge on the anion compared with a cation having 8 electron configuration. Thus, a cation with 18 electron configuration will lead to higher polarization of the anion. This can be easily demonstrated by comparing the ions of same size N positive and Cu positive. The sodium ion Na positive has the configuration 2s2 2p6, while Cu positive has 18 electrons configuration 3s2 3p6 3d10. Since Cu positive ion polarize the anion to greater extent than Na positive, the copper halide CuCl is slightly covalent and is therefore insoluble in water. On the other hand, NaCl is ionic and is highly soluble in water. The covalent character of CuCl is further supported by its low melting point 705 Kelvin compared to 1073 in case of NaCl. Similarly, Hg2 positive with the electronic configuration xenon 4f14 5d10 and Ca2 positive with the electronic configuration 1s2 2s2 2p6 3s2 3p6 have similar ionic radii. Hg2 positive with the pseudo-noble gas configuration is more polarizing and consequently its compound HgCl2 is more covalent than those of Ca2 positive. This is evidenced by the low melting point of HgCl2 549 Kelvin compared to CaCl2 1045 Kelvin. Next heading 4.11, defects in crystal structure. In an ionic crystal, the ions are arranged in a completely regular three-dimensional pattern. A crystal is considered to be perfect or ideal if the constituents, molecules, atoms, or ions are on their correct lattice position in the structure. In fact, a crystal is ideal only at the absolute zero temperature, that is at 0 Kelvin. At temperature higher than 0 Kelvin, there is a considerable degree of thermal vibrations. As a result, the arrangement of the atoms, molecules, or ions hardly remains perfect, and the crystal is considered to have disorder or defects. There are two types of defects in the crystals, which are A. Defects in stoichiometric crystals, B. Defects in non-stoichiometric crystals. A. Defects in stoichiometric crystals. Stoichiometric compounds are those compounds in which the number of atoms or ions present are exactly in the ratio indicated by their chemical formula. These compounds obey the law of constant composition. Such compounds were originally named as Daltonide compounds. Two types of defects there are observed in stoichiometric crystals known as Schottky and Frankel defects respectively. Schottky defect. Schottky defects consist of a pair of holes in the crystal structure, that is, one positive and one negative ion are absent. The number of cation vacancies and anion vacancies have to be equal in order to maintain electrical neutrality. This type of defect generally occurs in highly ionic compounds where the size of the cation and that of the anion are generally similar. It is observed that the coordination number of the ions is generally higher, 6 or 8. Crystals which predominantly show Schottky defects are NaCl, CaCl, KCl, and KBr. For a 1:1 solid Mx, a Schottky defect consists of a pair of vacant sites, that is, a cation vacancy and an ion vacancy. Schottky defect for an Mx2 type structure will consist of the vacancy caused by the M2 positive ion together with 2x negative anion vacancies, thereby balancing the electrical charges. Frankel defects. A Frankel defect consists of an atom or ion moving into an interstitial position, thereby creating a vacancy. Metal ions are generally smaller than an ion. It is therefore easier to fix the cations into the alternative interstitial positions. This type of defect is generally observed in cases of where there is a large difference in size between the positive and negative ions. In other words, Frankel defect is more common in crystal where the coordination number is usually low, 4 or 6. Example of compounds displaying Frankel defects are ZNS, AgCl, AgBr, etc. The defects found in the crystals are sometimes blessing in disguise. Some of the consequences of the defects in the crystal are: first, that the crystal may conduct electricity to small extent. Crystals with Frankel defects have only one type of hole, whereas crystals with Schottky defects have holes from positive and negative ions, and conduction may arise by using either one type of hole or both types. Second, the presence of holes in the crystal lowers the density of the crystal in case of Schottky defects. Third, the presence of holes decreases the stability of the crystal and thereby the lattice energy may also decrease. Fourth, the presence of ions in the interstitial sites may expand the lattice and increase the unit cell dimensions. Fifth, the closeness of similar charges in the Frankel defect increases the dielectric constant of the crystals. B. Defects in non-stoichiometric crystals. Non-stoichiometric compounds are those compounds in which the ratio of the number of atoms of one kind to the number of atoms of the other kind does not correspond exactly to the ideal whole number ratio as given by the formula. Such compounds do not obey the law of constant composition. Common examples of non-stoichiometric compounds are the oxides and sulfides of transition elements, example FeO, FeS or CuS. If the ratio of the atoms is not exactly 1:1 in the above compounds, there must be either an excess of metal ions or a deficiency of the metal ions. For example, in case of FeO, the composition may be Fe0.840, Fe0.940. Since electrical neutrality is always to be mentioned, this can be done either by having extra electrons in the interstitial sites or by changing the charge of the metal ions. Such type of compounds contain defects known as non-stoichiometric or Berthollet compounds. Metal excess. Non-stoichiometric defects due to metal excess may occur in two ways. Anion vacancies. This type of defect may arise because of the absence of a negative ion from the lattice site, thereby increasing in the cation metal concentration. This leaves a hole which is occupied by the electron, thereby maintaining the electrical balance, as shown in figure 4.35. This defect is similar to the Schottky defect because it arises due to the hole and not due to interstitial ion. This type of defect is generally introduced into the crystal when compounds such as NaCl, KCl are heated with excess of the vapors of their constituent metals, or when the crystals are treated with high energy radiations. On heating the crystals in the presence of sodium or potassium vapors, the crystals become deficient in the negative ions, and their formula can be represented by AX 1 to curl, where curl is the small fraction. It is important to note that non-stoichiometric form of NaCl is yellow in color. The yellow color is obtained because the electron is trapped in the lattice. These electrons are called F centers. F stands for Farb, which is a German word for color. Extra cation occupying the interstitial sites. The defect arises when the non-positive ion is missing from the lattice site. The corresponding excess cation associated with the metal moves to occupy the interstitial site. As an example, when zinc oxide is heated to lose oxygen and turns yellow in color, in fact the zinc ion moves to the interstitial site. ZNO in presence of heat gives out X upon 2 O2 plus ZNO 1 to X. This type of defect is similar to Frankel defect in that the ions occupy the interstitial sites. This kind of defect is more common and is formed in crystals which would be expected to form Frankel defects. If you recall, Frankel defect are formed in crystals where the ions are appreciably different in size and possess low coordination number. It is important to note that crystals with other type of metal excess defect contain free electrons, and if these migrate they conduct an electric current. There is a small number of such defects in the crystal, and consequently the number of electrons are also small. The amount of current carried by small number of electrons is also small, and therefore crystals with metal excess can be ideal candidates for semiconductors or n-type semiconductors. Metal deficiency. Metal deficiency compounds can be represented by the formula 1 M1 to X, where rho is the small fraction. Metal deficiency can arise in two ways in both the types. The metal is in the variable oxidation state. Thus, these defects arise in transition metals which are known to exhibit different oxidation states. Let us discuss these due to first, cation vacancies. If the cation is absent from the lattice site, the charges can be balanced by an adjacent metal ion having an extra positive charge, as shown in the figure 6.37. The commonly found examples of compounds having this defect are FeO, NiO, FeS, and CuI. Let us take an example of FeO. If one Fe2 positive is missing from the lattice site in FeO, then there must be two Fe3 positive ions somewhere in the lattice to balance the electrical charges. Similarly, if a Ni2 positive ion is missing from the lattice in NiO, there must be two Ni3 positive present in the lattice. Second, excess anions occupying interstitial sites. Metal excess defects can be generated if extra anions occupy the interstitial sites. These extra negative charges balanced by the extra charges on the adjacent metal ions higher oxidation state. This is shown in figure 4.38. Since the negatively charged ions are usually larger, it is difficult for them to be accommodated into the interstitial sites. As a result, no example of crystals containing such negative interstitial ions are known at present. Next heading 4.12, bonding in metals, metallic bonding. Metals are known to the mankind since ages. Of the 109 elements that have been named so far in the periodic table, more than 80 elements are metals. Metals are solids at ordinary temperature and pressure with the exception of mercury and gallium. The characteristic physical properties of all the metals are: they have characteristic metallic luster. They are malleable and ductile. They are exceptionally good conductors of heat and electricity. They form alloys. Their crystal structure are almost always cubic closed pegged CCP, hexagonal closed peg HCP, or body centered cubic BCC. Many of the properties of the metals, such as chemical reactivity, hardness, strength, melting and boiling points, can be explained with the strength with which the atoms of the metal are held together. The force of attraction that binds the atoms of metal together is called metallic bond. This binding strength can be measured by the energy required to break the metal into the gaseous atoms, that is, atomization energy. Thus, metals with low atomization energies generally are soft and have low melting points, whereas metals with high atomization energies are hard and have high melting points. The heats of atomization decreases on descending a group in the periodic table. It suggests that the heat of atomization is inversely proportional to internuclear distance. Interestingly, the heats of atomization increases across the periodic table from group 1 to group 2 to group 13 as shown in the table 4.15. It means that the strength of metallic bonding is related to the number of valency electrons. Group 1 metals have the outer electronic configuration ns1 and thus has only one electron for bonding. Group 2 metals have the outer electronic configuration ns2. On excitation, the outer electronic configuration becomes ns1 and p1 with two unpaired electrons which can form two bonds. Similarly, group 3 metals on excitation has the electronic configuration ns1 and p2 and thus can use 3 electrons for metallic bonding. The melting and boiling points show similar trend as in case of atomization energy. It is important to note that the metallic bonds are much stronger than the weak van der Waals forces that hold the discrete covalent molecules together in the solid state. In brief, the bonding energy of the metal depends upon the average number of unpaired electrons per atom available for bonding. The crystal structure of the metals has been found to depend upon the average number of unpaired s and p orbitals per atom involved in bonding. When the number of bonding sp electrons is less than or equal to 1.5, the body centered cubic structure is observed. When the number of bonding sp electron is between 1.7 and 2.1, the hexagonal closed pegged HCP structure is observed. When the number of sp electrons is in the range 2.5 to 3.2, the cubic closed pegged structure is observed. Similarly, when the number of sp electrons is near 4, a non-metallic diamond-like structure is found. All these observations can be summarized in the table 4.16. The dependence of structure on the number of p electrons is more important compared to s orbitals and d orbitals. This is because p orbitals are highly directional in character. Accordingly, all the alkali metals have BCC structure. However, only beryllium and magnesium of the alkaline earth metals strictly have the HCP structure. The BCC structure shown by calcium, strontium, and barium can be easily explained by the general rule that the relative importance of d orbitals increases with the atomic number. In fact, excitation of ns2 electrons to n-1d ns state is energetically more favored over excitation to the ns np state. The BCC and HCP structure shown by scandium, yttrium, and lanthanum in contrast to normal CCP structure of aluminium can be explained in terms of d orbital participation as in case of calcium, strontium, and barium. In the second half, In the second half of the transition series, the extra electrons may be put in the p level to avoid pairing of d orbitals. This allows the maximum participation of d orbitals in metallic bonding. This increases the number of s and p electrons involved in metallic bonding. For example, in the group copper, silver, and gold, the excited electronic state involved in bonding is probably d8 s1 p2 instead of d10 s2. This involves the participation of 5 bonds per atom, 2 from d orbitals, 1 s orbital, and 2 p orbitals. Consequently, copper, silver, and gold acquires CCP structure. In zinc, Z is equal to 30, 3d10, 4s2. All the d orbitals are full. The excited state of zinc used for bonding is 3d10, 4s1, 4p1, giving 2 bonds per atom, and the body centered structure is justified. To summarize, the bonding in metals has two important features. First, the bonding energy of metal depends upon the average number of unpaired electrons available for bonding on each atom. Second, the crystal structure adopted depends upon the number of s and p orbitals preferably p orbitals on each atom that are involved with bonding. Next, heading 4.13, theories of bonding in metals. A number of theories have been proposed to explain the bonding in metals. The bonding in metals is called metallic bonding. Metallic bonding is neither covalent nor ionic. Let us explain the various theories proposed to explain the bonding in metals. First, free electron theory. Free electron theory considers metals are as consisting of metal ion at fixed positions in a sea of mobile valence electron as shown in the figure 4.39. The metal ions are held together in a crystal by the attraction between the positive charges of the metal ions and the negative charges on the mobile valence electrons. The mobile valence electrons are delocalized over the entire crystal. Because the valence electrons are free to move, metals are good conductors of heat and electricity in both the solid and liquid state. When a metal is heated, the positively charged metal ions called the kernels vibrate more vigorously about their fixed positions in the crystal. Because of their movement, the metal ions effectively occupy more space in the crystal and interfere in the way of mobile valence electrons. As a result, electrical conductivity of the metal decreases with increased temperature. The free electrons theory is also named as electron sea model. This model is also helpful in explaining why metals are malleable and ductile. Malleable means capable of being shaped by hammering or spread out in sheets, whereas ductile means capable of being drawn into wire. When one layer of a metal crystal is moved over the other, the positive charge on the metal ion are shielded from each other by the valence electron as shown in figure 4.39. This model also explains successfully the metallic luster of metals by absorption of photons of electromagnetic radiation by the mobile electrons and subsequent re-emission of the energy as light. Second, valence bond theory. The credit for the development of valence bond theory goes to Linus Pauling. It is based upon the principle of electron pairing to form covalent bonds between atoms in a metal by sharing of electrons. This is similar to one we have already discussed in the formation of covalent bonding in compounds. There is, however, one important difference in the bonding between metals and compounds. In metals, there are not sufficient number of electrons to form two electron covalent bonds with all the nearest neighbors. It means that the bonding in metals is short of electrons and is referred to as electron deficient. Let us take an example of lithium metal which crystallizes in a body-centered cubic lattice. Each lithium atom in this arrangement is in direct contact with 8 other lithium atoms. Lithium atom is known to form a covalent bond with other lithium atom by sharing one 2s valence electron. Since each lithium atom can form 8 bonds with other atoms, a total of 16 electrons are needed to do this. However, there are only 9 valence electrons available, one each with every lithium atom. As a result, normal covalent bonds are not formed with all the neighboring lithium atoms. In order to account for the bonding of the central lithium atoms with all its neighbors, Pauling suggested the idea of delocalized bonds. Accordingly, different resonating structures can be proposed involving bonding between different atoms, and the true structure is the resonance hybrid of these structures. A particular arrangement of bonding of lithium atoms is one of its resonance forms. Some of the contributing structures are shown in figure 4.40. It is clear from the figure 4.40 that ionic structure can also be written. This is because lithium atom has a low ionization energy, and consequent to that it can ionize and can form ionic structures as well. However, this will require the presence of vacant low energy orbitals in the other lithium atom to accommodate the extra electron. Lithium atom has vacant 2p orbitals which do not differ much in energy from 2s orbital. Therefore, it can form lithium negative ion. Thus, there are several resonating structures, and the true structure is a resonance hybrid of the different resonance structures. We know that more the resonance structures one can write, greater is the stability. Consequently, the system becomes more stable. This means that the cohesive forces which holds the structure together is large. In metallic lithium, the cohesive energy is 3 times greater than in conventional Li2 molecule. The cohesive energy increases from group 1 to group 13. This is explained by the atom capable of forming in the cohesive energy increased number of bonds. In addition, it gives an extra large number of possible structures. The presence of ions could easily explain the electrical conduction. However, this theory fails to explain the conduction of heat in solids. Thus, the valence bond treatment given by Pauling is very useful in explaining bonding between atoms in metals qualitatively. However, the theory fails to supply a quantitative explanation to the properties of metals. Third, molecular orbital theory of bonding in metals, band theory. Molecular orbital theory provides a more comprehensive modeling of metallic bonding. This model is called the band theory and explains the properties of metals more quantitatively. We have already learned that two lithium atoms combine in the gas phase and form a dilithium molecule Li2. The molecular orbital diagram showing the mixing of two 2s atomic orbitals is shown in figure 4.41. Bonding occurs in Li2 molecule because sigma 2s bonding MO is full and the corresponding anti-bonding orbital is empty. Suppose three lithium atoms combine to form Li3. In that case, three 2s AO atomic orbitals will combine to form three molecular orbitals, one bonding are non-bonding and one anti-bonding. The energy of the non-bonding molecular orbital is in between that for the bonding and the anti-bonding orbital. Thus, the three valency electron from three lithium atoms would occupy the bonding MO 2 electrons and non-bonding molecular orbital 1 electron as shown in figure 4.42. Let us consider four lithium atoms. The 4 AO would combine to form 4 MOs. Two of the molecular orbitals will be bonding and be other two anti-bonding. It is important to note that the presence of two non-bonding MOs between the bonding and the anti-bonding orbitals reduces the energy gap between the orbitals. The 4 valency electrons would occupy the two lowest MOs, which are both bonding orbitals as shown in figure 4.42. As the number of electrons in the cluster increases, the spacing between the energy levels of the various orbitals decreases further. When there are large number of atoms, the energy levels of orbitals are so close together that they form almost a continuum. A group of very closely spaced energy level is called a band. A difference in energy between the bonding and anti-bonding molecular orbital is called the energy gap. It is important to note that the energy gap is smaller when more and more atomic orbitals of lithium are combined than when only two lithium atoms are combined. We have already discussed in chemical bonding that the number of MOs must be equal to the number of participating AOs. Since there is only one valence electron per atom in lithium and a MO can hold two electrons, it means that only half of MOs in the 2s valence band are filled. That is the bonding MOs. It needs a very small amount of energy to excite an electron to an unoccupied molecular orbit. The molecular orbitals extend in three dimensions over all the atoms in the crystals. As a result, all the electrons have high degree of mobility. It is the mobility of electrons that accounts for the high electrical conduction of metals. Thus, lithium is a good conductor. If one end of the piece of metal is heated, electrons at that end gain energy and move to the unoccupied molecular orbitals where they can travel rapidly to any part of the metal. Consequently, the other part becomes hot. This explains the thermal conduction of metals. The electrical conduction takes place similarly. A small input of energy can cause electrons to move from the filled portion of the band to the unfilled portion. In the absence of an electric field, equal number of electrons will move in all directions. However, if a positive electrode is placed at one end and a negative electrode is placed at the other end, then electrons will move towards the anode much more readily than in the opposite direction, and thus the electric current flows. Conduction occurs because of molecular orbitals extend over the whole crystal. This is effectively an energy gap between the filled and unfilled molecular orbital. There is no energy gap in case of lithium. It is because only half of molecular orbitals in the valence bond are filled with electrons as shown in figure 4.43. Let us now discuss the metallic behavior in case of beryllium with the electronic configuration of beryllium as BeZ is equal to 4 He2S2. Both sigma 2s and sigma star 2s molecular orbitals will be fully filled. It means that the band derived from overlap of 2s atomic orbitals will be completely filled. It appears that beryllium could not exhibit metallic properties because there is no space in the band in which the electrons can move about. However, the empty 2p band overlaps the 2s band because of this overlap of the bands. some of the 2p band is occupied and some of the 2s band is empty as shown in figure. On supplying small amount of energy, the electron can move into empty 2p orbitals. The electrons can therefore move easily, and this accounts for the metallic behavior of beryllium. Next, heading 4.14, conductor, insulators and semiconductors. We already know that semiconductors are materials that are able to conduct small quantities of currents. They are poor conductors than metals but are not insulators. Semiconductors are solids there where there is only a small difference in energy between the valence band electrons and the conduction band. The small difference in energy is called the band gap. The group 4 elements silicon and germanium have structures similar to diamond. However, in contrast to diamond, silicon and germanium are semiconductors. A question arises why these three structurally similar substances, diamond, silicon and germanium, have different conductivity. The answer lies in the size of the band gap, that is the difference in energy between the valence band and the conduction band. If an electron is promoted from the valence band to the conduction band, singly occupied states in the valence and conduction band are formed. In case of metals, there is no gap between the filled and unoccupied molecular orbitals. As a result, the electrons move freely even when a small amount of energy is supplied. In case of non-metals, the valence band is full and there is a wide energy gap between the valence band and the next empty band. As a result, electrons cannot be promoted to an empty level where they could move freely. Such elements are called insulators. Type of semiconductors. There is another class of materials where the bands are close enough to allow only a small amount of electron excitation in the upper unoccupied band. These elements are called intrinsic semiconductors. Pure silicon or germanium belong to this class of materials. Such elements constitute the border line between metals and non-metals in the periodic table. The energy gap between the valence band and the conduction band in semiconductor is quite small. Semiconductors have band gaps in the range of 50 to 300 kJ per mole. The band gap narrows as one descends in the group 4. In intrinsic semiconductors, the number of electrons promoted in the conduction band is governed by the temperature and the magnitude of the band gap. The smaller the band gap, the smaller is the energy required to promote a significant number of electrons. As the temperature increases, larger number of electrons can be promoted to the conduction band. Extrinsic semiconductors. Let us see how the impurities increases the conductivity of semiconductors. The conductivities of these material is controlled by adding small number of atoms of different kinds of impurities called dopants. In order to answer this question, let us consider the most widely used semiconductor, silicon, which has become the backbone of modern technology. The structure of silicon is the same as that of diamond. An atom of arsenic radius 125 ppm is nearby the same as that of an atom of silicon radius is equal to 118 picometer. Consequently, atoms of arsenic can be replaced by some atoms of silicon in the crystal of silicon. However, an atom of arsenic has 5 valence electrons, one more than present in silicon. The extra electron can move through the crystal if an electric current is applied. A semiconductor in which the current is carried by the movement of negatively charged electrons is called an n-type semiconductor. Similarly, if an atom of boron is substituted for an atom in silicon, there is a shortage of one electron. As a result, electron deficient hole is created in the crystal. On the application of electric current, an electron moves from neighboring bond to the filled hole. This creates a new hole. Such type of semiconductor in which the current is carried by the movement of positive electron deficient holes is called p-type semiconductors. Weak interactions. Next, heading 4.15, van der Waals forces. We know that all the gases condense to liquids if the temperature is very low and the pressure is very high. It suggests that there must be some kind of attractive forces operating between the gas molecules. These intermolecular attractive forces are called van der Waals forces. Intermolecular attractive forces are not as strong as intermolecular forces. In fact, intermolecular attractive forces are the forces inside molecules that hold the atom together. In other words, intermolecular attractive forces are called chemical bonds. It is better to differentiate between the intermolecular and intramolecular attractive forces by taking an example of bromine molecule. The bond holding the two bromine atoms together in a molecule is the intramolecular attraction. The force holding the two bromine molecules together is an intermolecular attraction. The energy is required to break covalent bonds ordinarily range from 150 to 800 kilojoule per mole, whereas the energy required to overcome intermolecular attraction are normally of the order of 1 to 40 kilojoule per mole. The strength of intermolecular attractions decreases rapidly with increasing distance between molecules. Therefore, intermolecular attractions are not very important in case of these gaseous molecules where the molecules are far apart from each other. However, intermolecular forces are important in liquids and solids where molecules are close together. Van der Waals forces are of three types: dipole dipole or Keystone forces, dipole induced dipole forces, London forces, instantaneous London instantaneous induced force. Dipole dipole attraction of force. These types of forces occur in molecular solids which have polar molecules such as HCl, H2O, NH3, etc. Consider HCl as an example. The electronegativity of fluorine 2.8 is greater than electronegativity of hydrogen 2.1. As a result, the bond between hydrogen and chlorine in hydrogen chloride molecule is polar. A polar molecule has a positive and a negative end. In the liquid and solid state, molecules are touching one another. The positive end of dipoles are attracted towards the negative end of dipoles in other molecules as shown. It is important to point out that the positive and negative charges on hydrogen and chlorine are only partial charges. Therefore, the dipole-dipole attraction between hydrogen chloride molecules is not nearly as strong as the attraction between Na positive ion and Cl negative ion, where have full plus or minus charge. This is the reason why HCl is a gas under ordinary condition, whereas NaCl is a solid with high melting point. The intermolecular forces between the dipoles are electrostatic attractions between opposite charges. The greater the dipole moment of the molecule, the greater is the force of attraction. This effect was studied in 1912 by Keystone and is popularly referred as orientation effect. Dipole induced dipole forces. Many important molecules such as O2, N2 and halogens are not polar. However, when these molecules come in the neighborhood of other molecules or ions which are polarized, and induced dipole appears on these non-polar molecules, the forces existing between dipole and induced dipole are called dipole-induced dipole forces. Let us see how a polar molecule such as water can induce a dipole in a molecule that do not have a permanent dipole. The classical example is the solubility of O2 gas in water. Let us imagine a polar water molecule approaching a non-polar O2 molecule as shown in figure 4.47. The electron cloud of the isolated gaseous O2 molecule is symmetrically distributed around two oxygen atoms. As the negative end of the polar H2O molecule approaches, the O2 electron cloud gets distorted. During this process, the O2 molecule itself becomes polar, that is, a dipole is induced in the otherwise non-polar O2 molecule. The result is that H2O and O2 molecules are now attracted to one another weakly. Oxygen can dissolve in water because a force of attraction exists between a permanent dipole and the induced dipole. This type of interaction were studied for the first time of Debye in 1920 and are popularly named as induction effect. Instantaneous dipole, instantaneous induced dipole or London forces. Iodine I2 is a solid, not a gas, as at STP. It means that non-polar molecules also experience intermolecular forces. In addition, non-polar molecules like H2, Cl2, Br2, etc. also condense to liquid if the temperature is low and the pressure is high. Attractive forces that exist between non-polar molecules are called London forces or dispersion forces. To understand how non-polar molecules can attract each other, it is important to note that electrons in atoms or molecules are in a state of constant motion. On average, their electron clouds are spherical as shown for O2 in figure 4.47. When two non-polar atoms or molecules approach each other, however, attraction and repulsion between their electrons and nuclei can lead to distortions in their electron clouds. It means dipoles can be generated momentarily in neighboring atoms or molecules. It is these induced dipoles that leads to intermolecular attractions. Thus, London forces are the attractions between molecules that results from the temporary dipoles caused by the movement of electrons. Chemists also call such forces as London or dispersion forces. London forces between helium atoms are very weak. This is because there are only two electrons in one s orbital of helium. The size of helium atom being very small, the movement of electrons in the region is localized only in the relatively small space. As a result, the electrons are strongly attracted to the nucleus. In addition, the distribution of charge in the helium atom cannot be unsymmetrical because the two electrons repel each other. However, this situation in case of xenon, which is very large sized and have 54 electrons around the nucleus, is very different from that of helium. In fact, the outermost electron in case of xenon are in the fifth shell, which is far away from the nucleus compared to helium atom. The attraction between the positively charged nucleus and negatively charged electron decreases very rapidly as the distance between the unlike charge increase. The size of fifth shell is much larger than the first shell when the outer electrons have sufficient room to away without getting too close to each other. The outer part of the charge cloud of xenon atom is much more easily pulled out of space, that is distorted, than the charge cloud of helium atom. Thus xenon is said to be more polarizable than small sized helium atom. The temporary dipoles, that is induced dipoles of xenon, are much stronger than the temporary dipoles in helium, and as a result xenon must be cooled only to 166.1 Kelvin minus 107.1 degree Celsius at atmospheric pressure to make it condense to liquid xenon, whereas it must be cooled at 4.3 Kelvin minus 268.9 degrees Celsius to make it condense to liquid helium. Thus, greater the number of electrons and farther the outer electrons are from the nucleus, the more polarizable are the other electrons, and higher the temperature at which the gas can be condensed to a liquid. The outer electrons in many molecules are sufficiently polarizable that the substance are liquids or solids at room temperature. The best known example are liquid bromine and solid iodine. In the light of above discussion, it will not be out of place to justify the melting and boiling point of noble gases. It is clear that with the increase in atomic number, that is, with the increase in number of electrons, there is an increase in the melting and boiling point accordingly to London forces. The three types of intermolecular forces discussed above are collectively referred to as van der Waals forces. In all these interaction, the potential energy of attraction varies as the inverse sixth power of the distance between molecules. It is expressed as E is equal to minus K upon R power 6, where K is equal to constant of proportionality and the negative sign indicates the force of attraction. The magnitude of each type of interaction varies depending upon the type of molecules. Inert gases have only dispersion forces, whereas the polar molecules possess all the three types of forces. Next heading 4.16 Hydrogen bonding. Molecules in which hydrogen is bonded to nitrogen, oxygen or fluorine have exceptional properties. A natural question arises, why do these molecules have typical properties? One can easily see this by examining the boiling points for compounds of elements in group 14 through group 17 as shown in the figure 4.48. Generally, the melting and boiling points of related compounds for a related series of compounds increase as the atoms get larger and larger because of the increase of dispersive or London forces. Thus, we have extrapolate the boiling point of H2TE, H2SE and H2S. One would predict the boiling point of water should be about 100 degrees Celsius. However, the boiling point of water is plus 100 degrees Celsius. Similarly, the boiling point of HF is much higher than that would be expected by comparison with the pH3, AgH3 and SbH3, and similarly the boiling point of HF is much higher than HCl, HBr and HI. In order to answer the exceptionally high boiling points of H2O, HF and NH3, it is appropriate to examine the attractive forces operating between these molecules. The unusually high boiling point indicates the presence of strong intermolecular attractive forces in these molecules. Fluorine, nitrogen and oxygen are the most electronegative elements. Covalent bonds between hydrogen and these elements are more polar than most electronegative elements. Covalent bonds between hydrogen and these elements are more polar than more bonds between hydrogen and any other elements. The partial positive charge on hydrogen bonded to fluorine, oxygen or nitrogen is greater than the partial positive charge bonded to any other element. The partial negative charge on fluorine, oxygen or nitrogen bonded to hydrogen are greater than the partial negative charge on any other element bonded to hydrogen. Secondly, hydrogen is the smallest atom, and atoms of fluorine, oxygen and nitrogen, which are at the right side of the second row of the periodic table, are also smaller than atoms of any other elements except hydrogen. As a result of very large partial charges and small sizes of the atoms, dipole-dipole attractions between molecules with hydrogen fluorine, hydrogen oxygen and hydrogen nitrogen are usually strong. This strong dipole-dipole attraction in molecules that have hydrogen bonded to nitrogen, oxygen, or fluorine is called hydrogen bonding. The hydrogen bonding in hydrogen fluoride is easy to show on a paper because the hydrogen bonding structure is planar. Hydrogen bonds are generally indicated by dashed line as shown below. In hydrogen bonded substances such as HF, H2O, NH3, hydrogen is attached to one fluorine, oxygen, or nitrogen by a covalent bond and to another fluorine, oxygen, or nitrogen by a hydrogen bond respectively. The three atoms joined by a hydrogen bond usually lie on a straight line. The hydrogen is at about normal bonding distance from the atoms to which it is covalently bonded and farther than the normal from the other atom. Each HF molecule forms two hydrogen bonds. In other words, hydrogen acts as a bridge between two molecules, holding one molecule by a covalent bond and the other molecule by a hydrogen bond. As a result of hydrogen bonding, HF exists as a cluster of hydrogen fluoride molecules rather than as an isolated molecule and is represented as HFN. This clustering HF accounts for the higher melting point of HF. Hydrogen bond is weaker bond compared to the conventional covalent bond. It is about 10% of the strength of the covalent bond. Listed below are the strength of bonds compared with hydrogen bond. Many of the properties of water that make life worth living is because of hydrogen bonding. Imagine if there was no hydrogen bonding, H2O would have been a gas. If you recall, H2S, H2SE, and H2TE are all gases under ordinary conditions. Water is, of course, a liquid because of hydrogen bonding. In a series of related compounds, intermolecular attraction are stronger for larger atoms. Intermolecular attraction increases in order of HETE the highest, then H2SC, then H2S, and water should be a gas. The fact that water is a liquid can now be explained by hydrogen bonding. Each hydrogen in a water molecule can form a hydrogen bond to oxygen in another water molecule, and the oxygen can accept a hydrogen bond from two other water molecules as shown. Types of hydrogen bonds. There are two types of hydrogen bonds. First, intermolecular hydrogen bonding. Second, intramolecular hydrogen bonding. Let us first of all explain the intermolecular hydrogen bonding. Intermolecular hydrogen bond is formed between two different molecules of the same or different substances. Some of the common examples are A. Hydrogen bond between hydrogen fluoride molecules. B. Hydrogen bond between two carboxylic acids. C. Hydrogen bond between methyl alcohol and ammonia. Between chloroform and acetone, between formaldehyde and water. Intramolecular hydrogen bonding. When hydrogen bonding takes place within a single molecule, this is called intramolecular bonding. It may link two groups to form a ring structure. Some of common examples are O substituted benzene compounds. Orthonitrophenol displays intramolecular hydrogen bonding and this prevents intermolecular hydrogen bonding. If metanitrophenol and paranitrophenol intramolecular hydrogen bonding is not possible because of the size of the ring. However, intermolecular hydrogen bonding is possible in meta and paranitrophenol. Because of intermolecular hydrogen bonding in meta and paranitrophenol, there is some degree of association. This association accounts for the higher boiling point of meta and paranitrophenol, 290 degree and 279 degrees Celsius respectively, compared to that of orthonitrophenol, 214 degrees Celsius. Another example is that of orthohydroxybenzaldehyde. The hydrogen bond plays an important role in almost all biologically important molecules. For example, hydrogen bond occurs in both carbohydrates and proteins. The shape of large biological molecules such as proteins are determined largely by hydrogen bonding. The shape is thus the major factor in the properties of biological molecules. This was all about ionic solids.